transfer in engineering curriculum. So at the outset, I would like to inform you that this workshop is organized by the joint collaboration of BEEP and IIT Bhilai. And I would like to thank BEEP for extending their support to organize the workshop. The objective of this workshop is to bring together faculty members teaching at the UG and PG level at various reputed institutes across the country. And the major objective is to sensitize the educators and make them aware about the challenges and the need of building energy efficiency in India. It is expected that this workshop will be beneficial to inculcate fundamental knowledge of building physics and building heat transfer, especially in engineering educations or engineering graduates, among engineering graduates, because there we have found that it is lacking the most. And we want to inculcate these fundamental knowledge and basic understanding through our respected faculty members who have joined today. And we are joined by more than we are expected to join by more than 45 faculty members who are teaching across various reputed institutions across India at the UG and PG level, all the relevant courses related to building heat transfer or building energy efficiency. As far as this workshop is concerned, so today we will have 2 sessions where experts will throw light on the importance of building energy efficiency, some key concepts related to energy efficient buildings, building heat transfer, and building energy simulations involving case studies as well. I hope that these sessions are going to be a good learning experience for all of us, and we would like to have your active participation and interaction during all the sessions. So with this, I would like to declare the start of the workshop. And the first session which we have today is will be taken by Mr. Prasad Bhavre. So just a second. And so basically he will introduce us about the BEEP. And let me introduce Mr. Prasad Bhavre. So he has done his BTech in mechanical engineering from NIT Raipur and MTech in energy system from IIT Bombay. So he is associated with BEEP since its inception in 2008. He specializes in building energy simulations, energy monitoring, and renewable energy systems. And he has been instrumental in the development of Eco-Niwas Sanhita. And he's involved in building energy simulation for CERETs and performance monitoring activities and project management. So I would like to invite Mr. Prasad Bhavre to kindly introduce the Building Energy Efficiency Program BEEP and the initiative taken by BEEP in India. So Mr. Prasad.
Thank you, Dr. Udaraj. And on behalf of Indo-Swiss Building Energy Efficiency Project, I welcome all the participants to this workshop. And let me quickly go over a presentation where I would like to sort of set the context and introduce you to the Indo-Swiss Building Energy Efficiency Project and what we are doing in terms of building science education initiative under BEEP. I hope my screen is visible to everyone.
Yeah, it's visible.
Okay. So briefly, I will talk about the context and everyone is aware of it, but touching the base once again, and then introduction of the BEEP and what we are doing under building science education initiative, the BEEP. So I think this is quite the basic thing like the greenhouse gas effect. So solar radiation coming from sun, which is absorbed by the earth, some part is reflected back, and whatever is absorbed, that is emitted from earth surface. But like the due to some of the infrared radiation which is passing through the atmosphere, but some of the radiation is uh, absorbed and re-emitted in all direction by greenhouse gases, molecules, and clouds. So this affects the warming of Earth's surface and the lower atmosphere. And the main gases which constitute the greenhouse gas effect are the carbon dioxide is the main, and in addition we have the water vapor and methane also. If we look at the how much the concentration of CO2 is there and how it has increased over the year. So in 1960, it was around 320, which has gone up to 400 plus. So there has been a steady increase in the CO2 concentration in atmosphere, and therefore there is an increase in greenhouse gas effect. And what you see the impact on the global average temperatures here in the bottom graph. So it has increased by like from 1860 to 2020, it has increased by about 1.2, 1.4 or so. So when we talk about GHG emission and CO2 emission, how the buildings are correlated with that. So in buildings, there are two major sources of CO2 emission. One, which is involved in manufacturing of building material, steel, cement, aluminum, all these require a very high energy to produce them. And therefore, they are also involved in the CO2 emission. And the more important part is the operation of building and the energy required for that. So heating, cooling of building, lighting, equipment, appliances, all consume energy, and in turn, they are responsible for CO2 emission. If we look at the how much the building sector contributes to CO2 emission. So roughly the study suggests that it constitutes around 39% of the global CO2 emission. So it is more than combined the building material and building operation is the highest, even as compared to the transportation or even as compared to the industry. So buildings are the major source of CO2 emission, and therefore a greater opportunity also lies in building sector to reduce it. If we look at the building sector and looking at the built up area estimates, so it suggests that in 2012, the residential built up area was about 13.4 billion square meter, while the commercial was 0.75. And it is expected that like there are various projections, so you may or may not reach to that level. It could be less. It may not be the same, reach to the same level. But what it suggests that there is going to be a good pace of construction, and we are going to have a lot of built up area coming up in next few years or 1 or 2 decades more. If we look at India and look at the electricity consumption in the buildings, so if you see in 2017, the total consumption was 1066 terawatt hour, and the contribution of building sector is roughly 1/3, so 33%. But if we look at the projection for 2030, then while the overall energy consumption will grow up, but the important thing to look at this contribution of building sector. So residential and commercial building will almost contribute to half of the electricity consumption. So it will sort of exceed industrial sector also. So if we think like what are the main reason for this rapid increase in energy consumption, then we find that just okay. Yeah. So the main reason is for this anticipated energy increase in energy consumption is the penetration of room air conditioner in the buildings. So if we look at the projections in 2010, the electricity consumption was hardly 10 or 15 billion kilowatt hour, which is likely to reach 500 plus billion kilowatt hours by 2050. So there is a steep rise expected in use of residential air conditioning systems, and that will contribute to a large amount of CO2 emission as well. So it is the CO2 emission is almost goes in hand with the similar kind of increase with the energy consumption. So and it also needs that the generation capacity should be increased considerably. So roughly the number suggests that about 150 gigawatt of electricity generation capacity will need to be added in the electricity distribution system. Yeah, so that was on the energy part, but the more important part is the thermal comfort and how like buildings like can provide thermal comfort, and how the thermal comfort impacts health and socio-economical aspects. So if we look at like the human body, so the normal core body temperature should remain between 36.5 to 37.5. If it increases slightly, then we feel hot, and then if it goes beyond 44 degree, then it causes the death. So so it is important to keep keep the temperature within those within the range, so that it causes minimum discomfort to the human. The other important fact is that in India, the majority of household, they do not have access to air conditioning system. So more than 90% will not have access to air conditioning system, although it is projected that air conditioning penetration is likely to increase. But right now, it is not, it's small. And like providing thermal comfort in building design is very important to make the buildings comfortable and occupants comfortable. So as the room temperature and wall surface temperature approach around 35, then the ability of human body to lose heat reduces drastically, and which will cause thermal discomfort. So that can cause a loss of concentration, nausea, irritability, muscle cramps, weakness, headache, etc. And then it also results in children not able to do study properly and loss of income due to poor productivity. So the thing is that if the housing design is done properly so that the indoor operative temperatures do not cross a certain limit, then then it then it can provide thermal comfort to the occupant, and then it will the situation that the operative temperature reaching 35-40 degrees Celsius will not occur if the design is done properly. Um, so so that was more about the context, and let me quickly introduce the project, Indo-Swiss Building Energy Efficiency Project. So it is a bilateral cooperation project between Indian and Swiss government with an overall goal of to reduce energy consumption in new commercial, public, and residential building in India through energy efficient and thermally comfortable design. The project started in 2011, and it will go up to 2022. We have got one more year due to pandemic issue to continue this project further for one more year. So this project has four component: building design, building technology, building policy, and outreach. I will talk about each of them. And under the building policy, there has been a sort of a big deliverable done by the project is the development of Econivas Samhita, which is the residential building code for energy efficiency for building envelope. So the part one was developed with the support of BEEP, which is on building envelope, and the next part has also been prepared, which is on which is part two, which is on electromechanical and renewable system. So coming back to the project components of BEEP. So the first one is building design, where we are working with the real life building projects and helping them to make them energy efficient and thermally comfortable. Also trying to monitor the performance so that the proposed performance is also realized. We are also developed an award scheme for energy efficient building design called Nirman. And also under this building design component, we have developed a CFD software, which is open source and free to use, and it will be available on the to the user shortly, maybe in next 3 to 4 weeks or so. And then also we have some other activities under building design, the BEEP student camp, so that will come later. And then we have the second component on building technology, where we are working mostly with building insulation material and external movable shading system. So we have done a performance monitoring study of external movable shades, and also quantified what is the measured saving, both in terms of energy consumption as well as improvement in thermal comfort. And then on building policy, we are working with Bureau of Energy Efficiency for the code development, what has already happened. We are working towards implementation of the code in the states. And then whatever knowledge is generated under this project, we are trying to disseminate through various activities. So this is all uh, covered in the fourth component of the project, education and outreach. So just to quickly show you, like the type of projects which we have supported, it's a public office building. The first one, it's then the second one is a school, hospital, um, affordable housing project, smart ghar, and an institutional building. So all of them, apart from the smart ghar project, uh, every all the other projects have air conditioning, and the idea was to reduce the energy consumption. And in smart ghar, the idea was to improve the thermal comfort without air conditioning system. And on building policy, as I said, we have worked with work for the development of part one of Eco-Niwas Samhita, which is on building envelope. We have also developed its compliance tool. It's a simple Java-based tool and does not require any installation and all. It can be run, and it is available on BEEP and BEE website both. And we have also developed a solution set for the combination of building envelope construction, which will help you to meet the requirements of the code. And then there was one study, quick assessment was done, that if this code is implemented gradually, then it has the potential of saving 100 million tons of CO2 by 2030. So coming back to the main part, where we are focused in during this event, is the Building Science Education Initiative under BEEP. So we have been doing various activities. So the first one is the BEEP residential BEEP student camp for architectural level, architectural and engineering student. And this we have done for last 3 years. And this year also it is going to be done in the month of December. We have developed a course and study material for undergraduate engineering and architectural student. And also we have a BEEP Youth Forum, which is a LinkedIn group for young professional, where they can interact on the subject building science, and get feedback from expert as well. So what we are doing, like at undergraduate level, building energy heat transfer is the one where we want to make impact in the engineering side. And on the architectural side, we have developed a course on building energy performance simulation. And as I already spoken about the BEEP student camp, which involved under which we have sort of trained about 150 students and young professionals. And then there is a BEEP Youth Forum. So the opportunity in this building science education sector is that more than 10,000 young professional architects and engineers enter the Indian construction industry every year. And majority of them are not oriented towards energy efficient building design. And that is where we see that there is a good opportunity, and we should try to we are trying to do activities at all level, undergraduate, postgraduate, and at professional level, to bring in the energy efficiency concept in buildings with the professional. So this is what we will be discussing today. the book, which is authored by Dr. Uday Raj, is titled as Building Heat Transfer, Understanding Through Numerical Example. So the background of this book is that we had uh, we had a meeting with the building science educators in December 28. And then in that meeting, it came out that there is a need of sort of a good numerical example related to building heat transfer so that people can understand how heat exchange happens in the building and how it affects the thermal comfort and all. So this is what all about I have to say. So looking forward to all your inputs, participation, comments, and yeah, thank you from my side. If you have any question, then you can let me know. So over to you, Dr. Udaraj.
Thank you, Prashantji. So if you have any question, please feel free to ask.
Good morning, Prashant sir.
Yeah.
Yeah, I am Mohammad Riazuddin from Tamil Nadu, Coimbatore, Sasi Creative School of Architecture. Sir, I have mentioned that architecture students and engineering students combined to got some classes regarding heat transfer, sir. So can you explain detailed about that particular class, because I am a faculty for architecture students, but I'm an engineer, so I can give some lectures on that, sir.
Actually, like for the BEEP student camp, so this we are organizing. This year will be the 4th edition of BEEP student camp. So we already have a kind of pool of experts and speakers who are who have presented in last three workshops. So the on the faculty side, we already have people on board, and like the in terms of student participation, that is also I would say is finalized for this year. But the thing is that the BEEP student camp is going to be the program. So Bureau of Energy Efficiency has shown a great interest in this program, and we are in touch with BE so that this BEEP student camp becomes a part of BE's program, and then BE continues to organize such type of events in the future for students. And there might be some requirement of faculty in, and it's in under discussion that they are saying that they would prefer to do it on regional basis rather than doing centrally at one place. So in that case, there would be definitely some requirement of faculty members in each region, and then we can propose names who are interested in this field.
Okay, thank you, sir.
Okay, is there any other thing? Okay, thanks, Prashantji. Okay, so So our next session is to be taken by Suklal sir. So he's heading Ashok B. Lal Architect Firm. So he did his graduation in Architecture Fine Arts from University of Cambridge, UK. He is associated with BEEP since 2013, and he has been a key technical partner supporting multiple activities of BEEP, such as IDP charrettes, development of Econivas Sahita, a BEEP student camp, MSIS design competition and studies, etc. He is also a member of JAC. So now I would request Ashok sir to take over and please start the session.
Thank you, Udayaraj. I will now share screen. You all can see my screen now?
Yes, sir.
Okay. So, welcome to this course. This particular talk that I am presenting to you is looking at what we call passive design strategies in the design of buildings and their integration with the electromechanical systems of buildings so that they become energy efficient buildings. So the important concept here is that it is not as though the design of buildings is one thing which somebody does and finishes, and design of the electromechanical systems, air conditioning, lighting, ventilation, etc., is another thing that somebody else comes and puts into the building to make it comfortable. The concept here is they are not separate things. They are to be seen as an integration of two systems. And it is when you actually integrate the two that you get the highest potential efficiency in the operation of buildings. So that's the basic concept here. It's a bit of common sense, but it's worth repeating. We know that buildings shelter the inside from an unpleasant outside. That is one of the purposes of any building design. When it is either too hot, too sunny, too cold, too windy, too dusty, if it is raining, and it is the building that we resort to seek protection from these conditions. Now, the outside is changing all the time. It changes from season to season, and it changes through the 24-hour cycle of the day and night. So the environment, the thermal environment, the conditions surrounding the building are changing constantly. But the building is by and large a static object. So the question for the designer is, how can one make this static object such that it keeps the inside comfortable? And we know that, generally speaking, the only thing that is variable in the building is its doors and windows, something that you can open and close. That's about it. And, we can see that in different climates, in different regions, according to what is available to people, people have built shelters, and then they have used different kinds of means to compensate for where the shelter is not adequate. In cold climates, it's often been a use of fire to warm up the inside, including inside the igloo, believe it or not. Now a building, as we know it today, most houses, most buildings have these components. As you can see on the right-hand side, there's a roof, there are walls, and there are openings, doors and windows. Can one end up making this static object stupidly, such that it becomes more unpleasant inside than it is outside? Is that at all possible? You would have thought, no, it's not. But here are some examples of how, in the name of progress and modern architecture, in the name of what we call world-class, very important buildings have been built using a lot of glass on the outside, as you can see here. Very important institutions, national level institutions, highly symbolic buildings, sending out a message to the world about progress and modernity. But these buildings are in effect solar cookers, because no matter what you do with the glass, no matter what type of glazing you may use, a lot of energy, a lot of the solar radiation, diffuse as well as direct solar radiation, enters through the glass into the building, and then it gets trapped inside. That is exactly how a solar cooker operates. And then it just begins to get hotter and hotter. And then, to be really modern, of course, we want air conditioning. You resort to air conditioning. You want to now turn a solar cooker into a refrigerator. Well, I mean, you could not be doing two completely opposite, polar opposite things, right? But this is what has been tending to happen. So how do you avoid this kind of thing? What we say is that we use passive design strategies in the design of the buildings, and these are methods of designing the building fabric itself, its physical structure, its walls, windows, roof, floors, etc., its physical structure and its configuration, that deploy the principles of building physics, which is the heat flow and heat transfer through the building fabric. They deploy these principles to maximize the duration of comfort and to minimize the duration of discomfort, so as to eliminate, if possible, or to minimize the need for additional cooling or heating using fossil fuel-based energy, which is what air conditioning or lighting today demands of us. So it's really about passive design strategies. The climate and its seasonal and diurnal patterns vary from place to place. So this is another kind of variable. We said that seasons are not static, seasons change. The temperature and things changes from day and night. But if you look at a building design, you might say that a building design in one place will be standardized, and then you could apply this building design, standard building design, to any place. Just take this building, because it has been designed to be optimized, you can take it anywhere. But that's not quite true, because these seasonal and diurnal variations, diurnal means the day and night variations, they also change from location to location. Surely, if you're in Delhi, you have a different climate compared to if you're in Bangalore. And if you're in Bangalore, you have a different climate compared to Chennai. Or if you're in Shimla, it's yet another something else. So the season and the diurnal variation depends on where you are on the planet, where you are in terms of altitude and distance from the sea, etc. Local climate matters. So, therefore, the passive design strategies that we talked about earlier would have to be responsive to that local climate. They would be climate responsive. And for that climate, the building design would respond to the seasonal and diurnal variations of that climate. The elements that you have to work with in your design are the shape of the building, the roof of the building, the walls and windows, including the direction in which the building faces in relation to prevailing breezes, which can be beneficial or could be very hot or very cold, and the direction in which the building faces in relation to the movement of the sun. Now, just to illustrate how different climates are, we are looking at the example of the climate in Delhi at the moment. So these two charts kind of summarize the climate, and they look at the variation in temperature from around the year, from January to December. They also look at the variation in radiation from the sky and from the sun, and also look at the humidity, the dry bulb and wet bulb temperatures at this, along the same graph. So you see the variations happening from January, February on to November, December in all of these parameters. So if you look at the temperature chart, what we notice is that the temperatures are highest during the month of May, right? And the temperature is the lowest during the month of January. It reaches, the bottom temperature. You'll also notice that the temperature varies during the day. So if you look at May, in the middle of the afternoon, the temperature can rise right up to 43, 44 degrees centigrade. But on the same day, at night, it could be coming down to 25, 26 degrees centigrade too, right? So what we are seeing is that during the dry season, when the relative humidity is low, you get a higher diurnal variation in temperature. But when the relative humidity goes up, like during the monsoons, the diurnal variation also comes down. It's less variation in temperature between the middle of the day and dawn. And also because of cloud cover, the radiation becoming much less, the temperature itself does not rise to the same level as during May. And then you can kind of understand how these temperatures and the radiation and the humidity are interrelated in producing the environmental effect that we call seasonal variation. What we see also in this graph is a gray band. You can see a gray band going from left to right. This gray band represents the temperatures in which people generally feel quite comfortable. So in the summer months, right up to 30, 31 degrees centigrade when it's fairly dry, with a bit of a ceiling fan on, we feel okay. It's all right with us, comfortable enough. And in the winter months, right down to 18 degrees centigrade, or rather, here it says around 23 degrees centigrade, but I know from my personal experience, right down to around 20 degrees centigrade, I would say with a bit of warm clothing on, I'm quite comfortable. So you can see that the degree to which the outside temperature diverges from the comfort band, which is the gray band, the degree to which that outside temperature diverges from it is the amount of work that the building has to do. The building has to reduce the impact of the outside on the inside so that the internal temperatures can be within the comfort band. That's the big message here. And you can also see that, well, during the, say, March and April, the average temperature is actually quite comfortable. It might be a little too hot if you went outside in the sun during the middle of the day. It'll be too hot. And it might be a little too cold if you were outside in the middle of the night. But if your building is heavy enough and the temperatures inside the building don't move too fast, then you'll find that the building inside is comfortable all the time. Same thing happens during the months of September, October, and November. And then going into December, you can begin to feel a little too cold. And going into January, yes, the nights do get too cold. And of course, during the months of late April, May, and June, you can read from these temperature graphs that substantial part of the day is above the comfort time, and the building may not be able to make you comfortable enough, even though you've deployed all the passive strategies. So it gives you some idea. And you can compare this with Srinagar. Of course, Srinagar is a cold climate. Much of the year, we are colder than comfort temperatures, right? And part of the year in the middle, say May, June, July, August, September, you're in the comfort zone. Again, if you design a building in such a way that it has sufficient building mass so that its heating up and cooling down is slow, therefore the indoor temperatures will tend to move towards the average temperature of the day and night. And therefore you can get fairly good comfort during the months of May, June, July, August, September without doing anything. And then when it comes to October, November, December, or January and February, the building itself is not able to do too much, but then you have the opportunity of catching a lot of sunshine. If there's sunshine outside, catch it and store the warmth inside the building. All right. So I'm just illustrating how, by reading the temperature graph, you can ask the question, what should my building do? Right? What should my building do for each season and for the characteristic of the temperature variations, the diurnal temperature variations in each season? But also looking at when it gets very humid, what would you like to have when it gets very humid? As we all know, you switch on the ceiling fan and you open the windows so that the humidity inside doesn't build up too much. So some common sense, but the exercise here is reading the temperature or the climatic information, which is very simple, just looking at these three factors, and then asking the question, what should my building be doing to remain comfortable inside the building? Fundamental of heat transfer. If you have any mass and it is surrounded by what we might call heat sources and heat sinks. So there are natural heat sources that surround a building, and there are natural heat sinks that can also be available to the building. So the natural heat source, of course, is the sun and the radiation from the sky. The natural heat source can also be the ground. So for instance, if you're in a basement, that is what is working. You are actually using the warmth of the ground to remain warm during the winters. And then the stability of the ground, the ground then becomes also a heat sink in the hot season, so that you can lose the heat into the ground during the hot season. So the ground acts as the ground and a water body in their relative temperature to the temperatures of the building or inside the building can act both as heat sinks or as heat sources. And you could say the same thing about ambient air. Usually the night sky is a heat sink. And you know, we have that scientific knowledge about if you look into the deep sky, the deep dark sky, you hit minus 273 degrees centigrade. That's a great heat sink. So when it's very hot, you can be losing heat into the sky at night very well. My battery is running low, so let me just please quickly connect. Yeah, I hope this is working. Oh dear, my battery is running low. And my plug point is not working too well. So let me just move on. What are the strategies? Let's move on a little bit more quickly. What are the strategies that we call passive strategies? In scientific terms, in physics terms, they are exposure to the solar and ambient air and wind adjacent and the adjacent microclimate. Exposure to the sun, ambient air, wind, and the adjacent microclimate. The second is insolation, which is the exposure to direct solar radiation. The third strategy is the heat transfer across the envelope of the building, the roof and the walls, as well as the windows. How does heat move from inside to the outside or from outside to the inside? Then there is the principle of heat exchange. Here, heat exchange means that there is some adaptation that is happening in the building. Either water is being moved through the building, or air is being moved through the building, or something is being opened so that it can lose its heat, or something is being done to capture the heat like that of the sun during the winter months. Then there's a question of humidity control, because humidity, high humidity in warm temperatures gives us discomfort. In cold temperatures, high humidity does not seem to give us the same discomfort. But in hot temperatures, when the temperatures are above 26, 27 degrees centigrade and the relative humidity rises above 65, 70%, you begin to feel very sweaty and very uncomfortable. So you control the humidity by either replacing the humid air by less humid air, letting it move, or simply the humidity on the surface of the skin can be controlled by just moving less humid air over the skin, taking off the moisture. And then, of course, eventually, this is not passive design, but eventually when you come to active design, you can draw out the moisture from the internal air to make it, to desiccate it by using electromechanical means. Then, of course, there's the use of heat sinks and heat sources and the application of what we call engines. I'll move on. So if you look at exposure, the most important thing in looking at exposure to the outside is seen here in a housing design. You can see there are lots of housing blocks, about 4 or 5 stories tall, and most of them are aligned such that their major longer face is facing towards the south or towards the north. Most of them are aligned like that. Now there is a reason for this. The reason for this is that as the sun rises from the east and then climbs over to the top and then sets in the west, if you look at the movement of these, or the solar geometry of the movement of the sun across the sky, and this data is available to us through many, many softwares, you can see that if you are to face east or west directly, you will be getting the worst of the rising sun as it hits at right angles into your building, both from the east and the west. But as it rises to the top, with a little bit of overhang over your windows, you can shade the windows, and the oblique angle of the sun on the surface, vertical surface of the building has much less impact. But then you also notice that the roof in the middle of the day gets the worst of the impact of the sun. But to reduce the impact of the sun during the early hours of the morning and the late hours of the afternoon, morning and afternoon, an orientation facing east and west in this case is beneficial, where you want to cut out the sun. But this is not always possible in all directions. So some of the buildings you'll notice here too are facing east and west, not the ideal thing. So you may have to do something special if you have to face the building east and west. Well, this is a closer look at buildings now facing east and west. All right, you can see the north sign symbol here, and you can see that some of the buildings are facing north and south, and some of the buildings are facing east and west. But then all of these buildings that face east and west, or for that matter, north and south, have a shading arrangement on their outer surface. And they will be all painted white. They'll be painted a very light color so that they can reflect off much of the incident radiation. Here they are. So you have a shading system that will enable you to cut out the light, the sunlight that you don't want entering into your windows. Another thing here is that this is a low-cost housing project on the left-hand side. And on the right-hand side is a more sophisticated project, but it's the same principle of a shading system outside that has been shown here. What the frames of the balcony and outside the windows indicate is that if you provide a frame like this outside the balcony and windows, then it is possible for residents to add a shading arrangement according to when they feel uncomfortable and when they want to open to the breeze and to the light. So a variable external shading system, no matter how you do it, simply economically, or you can nowadays automate it, but that is what is actually needed. That's where we are really going in passive strategies too. And an institutional project, that was housing, institutional projects. Here you can also see that all the long blocks have their long faces facing east and west, are facing north and south. And some blocks that connect these blocks, the longer blocks, are necessarily having to face east and west. But then what do? Whenever that happens, you have to add another layer of shading systems outside this, so that the direct impact of the rising and setting sun is cut out by an external shading system to reduce the impact of insolation. External shading systems, why and why not internal? Well, once the sun has entered into your room and the heat is being absorbed by the wall surfaces and the floor surfaces of the room has got heated up. And it'll be a task to get rid of that heat. So just drawing curtains across your window is not going to do the job. You really need to stop the sun outside your window, outside the external surface of the building, to be really effective. And another principle of what this type of shading should be is that anything that intercepts the sun will absorb some of its heat. It'll get heated up. And that heat, which is being absorbed by the intercepting membrane, whether it is a blind or a screen or whatever you have, or a louver, that heat should not be transferred back into the building. So that heat should be quickly dissipated. That means it should be lightweight, the membrane should be lightweight, it should be filigree, air should be able to move around it and through it to dissipate its heat quickly to the surrounding air, rather than conducting it into the building. And this system should be minimally connected to the mass of the building. It should not be integrally and heavily connected, because if it is integrally and heavily connected, then the heat that it is absorbing, the membrane is absorbing, will tend to be conducted into the building. Another point about exposure is the shape of the building itself. The more compact the shape, the less the exposed surface area in relation to the floor area of the building. So if you have a very long, narrow building or a building which has lots of ins and outs, so that its peripheral surface is very, very large in relation to the floor area it encloses, you are likely to have more surfaces that will be subject to heat exchange between the inside and the outside. So where you want to conserve heat, or you want to conserve air conditioning inside the building, let us say the coolth of the air conditioning inside the building, you actually want to reduce the degree of exposure through the outer surfaces of the building. So generally speaking, for air-conditioned buildings particularly, and for buildings in the composite and the hot-dry climates, certainly a compact shape is always more beneficial. Shading. I told you the principle of shading. Filigree, lightweight, minimally connected to the mass of the building. And the shading design can be derived from solar geometry, depending on which way the building is facing. It can be facing southwest, southeast, etc. It may not be facing directly due north or south. It depends on the location of the building and its geometry. But the shading system, with a careful study of solar geometry, can be devised to cut out the sun when you don't want it, but to let it in. Say in Delhi, you may want to let the sun in. Like nowadays here in November, December, it's quite pleasant to have the sun coming into the house or into the building. So the solar geometry of the fixed shading system can be actually worked out to be appropriate for that particular latitude and for that seasonal pattern. Also, once again, the ideal here would be an adjustable external shading system. That would be ideal. So that you can modify it according to the time of the day, according to your orientation, and according to the season. As it does to show in the same project, when you came to a different orientation, the geometry of the shading system changes. Another principle of reducing exposure, especially in the very hot climates, is that around the building, you try to create a microclimate. So this is an entrance courtyard into this building, which has a pool of water, which has some plantation and a shading screen. And it so happens that the top is an opening to the sky, which then on top of that opening, you have a solar PV array, which gives you shade. So shaded spaces, protected semi-open spaces, not exactly completely built up, semi-open spaces create a microclimate around the building, which can be beneficial, especially in hot climates. Following the same principle of reducing the exposure outside, here it is shown in housing design. Here is a plan of a housing block in which the adjacent homes are sharing walls, and it's really like a shared wall system, party wall system. Where if you have a row of houses along a length of a passage like this, then only the faces at the bottom and at the top are exposed, but the sides are protected. And it's only at the end of the building that the sides are exposed. So you actually get a fairly compact form with less exposure to the outside. So here's the message about design of the building itself. That the design of the building by its shape, by its orientation, is also responding to the climate. A residential building in the heart of the city in Delhi, here again a compact form taking the shape of the plot, and it has a small courtyard which is a shaded courtyard in the middle of it. And the outer face of the building has screens that can be moved to cut out the sun when it is becoming unpleasant. Here we have the example of adjustable outside shading screens. You can move them horizontally sideways. they're designed with some perforation to let in some filtered light, right? And to let in some air. On the sides, from the edges of the balconies, you'll still get some air, but you can cut out the direct sun entering into the glasses of the rooms behind. And these are adjustable. Apart from compact shape in the plan of the building, one can also think of a compact height of the building, because the degree of exposure or the extent of heat exchange that the building incurs with its surrounding areas is also a function of the height of the surrounding of the envelope walls. The taller the walls, the greater the area of heat exchange. The shorter the walls, the less the area of heat exchange. So one can certainly think of reducing the height of the building. And in careful design of structural systems, integrating the air conditioning system in a particular manner, you can do office buildings, which we have done, at 3.3 meters, 3.2 meters floor to floor, in place of what is the standard convention of 4 meters floor to floor. So you not only save the amount of construction material that you have to build with, but you also save on the exposure of the building to the outside. Well, integrating shading in glazing systems. Here's an example of how we did this, and also looking at the window sizes. A window is necessary. You want to be able to open and close the windows so that you can get ventilation. You want to be able to get daylight in. You want to be able to look out, look at the view. So windows will be part of building design. But you must size the windows with great care. Here, this was a design of an office building where on the external envelope, the window area is only 18% of the wall surfaces, right? And you get very good distribution of daylight. And from the seats in the office, through the small windows on the outside that you can see on the left-hand picture, you get a very nice view to the outside too, a kind of a release from the interior of the office. But the trick here is to reduce the window area, because no matter, compared to a wall which may be insulated, compared to an insulated wall, a window will always have greater tendency for heat transfer. The U value of a window, even when it is double glazed, is not as favorable as an insulated wall. So window area must be controlled. Then, of course, comes the insulation on the wall and the insulation on the roof. Roof being the worst affected because the sun beating down on it so hard when it is vertical above you, that needs the highest level of insulation. The ECBC, the Energy Conservation Building Code for residential buildings in Eco-Niwas Samhita, as well as the ECBC for commercial building, is now specifying what is the minimum performance of the roof in terms of insulation you must achieve. And in architectural design, in building design, you can do a bit more. You can create a more favorable microclimate. In this case, there's a fountain with tall towers of concrete, which are also fountains with water goes to the top and trickles around the surface of the concrete to cool down the concrete mass, and they become then cool bodies. They become cool bodies, which in effect then radiate the cool or draw the heat from the surrounding surfaces of the office building. So creating internal and surrounding microclimates with plantation, etc., is important. Another thing is the use of thermal mass in buildings. The heavier the thermal mass of the building, the longer the building takes to change its temperatures. And if my body living inside the building is exposed to the mass, the surfaces of this thermal mass, then I will also experience the radiant temperatures of this thermal mass. If the radiant temperatures are controlled and kept cool, then I will feel comfortable. Whereas a low mass building will quickly rise in temperature and quickly go down in temperature. will not be able to give you the benefit of what we call a flywheel effect in managing temperature variations. Thermal mass is another property that we need to take care of. And then, of course, when you're air conditioning or when it is very hot outside or very cold outside and the wind is blowing, you don't want that wind to, to blow through or the windows to be leaky. And you don't want the places where there are doors for entering into the building and exiting from the building to be exposed to the movement of air from the outside. So we resort to what's called an airlock lobby entrance, which is a space which has doors at two ends, one facing to the outside, one facing to the inside, so that the exchange of air between the inside and the outside is limited as people move in and out of the building. So here's the big thing, big picture. The building energy consumption, the consumption of energy in the building is, of course, a factor of climate. In order to deal with it all, you don't only respond to the climate in architectural design, where you look at the building envelope, but there are other factors that contribute to the heat inside. It is the number of people who inhabit the building, the number of users. It is what they do inside the building. For instance, if it is an industrial building where lots of stuff is happening, there's heat is being produced. If it's a gym, a gymnasium, where people are very active, lots of heat is being produced. And it would be, if it's an office building where there's lots of computers, heat is being produced there. Then, if artificial lighting is being used to light up the spaces, that is also producing heat. And this then, you have to then combat with HVAC or electromechanical means. So it's really looking at all of these things together simultaneously in the process of design that gives you the best possible results. So here's an example of how we did it in a particular building. Microclimate, there's a courtyard with a fountain. The roof is planted with, and the surrounding spaces are gardens around this office building. And you can see there's a pergola in front with creepers growing over it and around it. The building height is controlled. And here you can see the relationship between the building and the surrounding greenery. It was going to have a slow solar PV array on top, which has not happened, but it has a flourishing lawn and garden on the rooftop. There's a detail. Now, of course, we have the technology and the means available to make sure that you get good waterproofing and you can still grow a garden on the roof. Very good method, actually. The outside walls are designed as boxes, which are insulating boxes made of a sandwich of concrete and insulating thermocol. And these boxes carry the air conditioning system. So they become storage. They also become shading system for the windows. They also become light shelves for reflecting the light into the ceilings. And the same system of walling is performing a number of functions for the building. Even the base of the building is insulated, and the places where there are no windows in the wall, that also has insulation. This is an air-conditioned building. More details of how this is done. How these technologies are developing quite rapidly. People are getting used to them, and people are finding how to integrate them into building design. I think that's the important point. The properties of the external wall and the windows are key elements in building design. In this building, the heavy mass of the floor slabs is embedded with radiant cooling pipes. So, as you can see in the right-hand picture, there are cooling pipes that are embedded in the concrete, and these cooling pipes are connected to an air conditioning system, the temperature that is running in these pipes the water temperature that is running in these pipes is around 16 degrees centigrade, not very cool, but it cools the slab down to a temperature which produces comfort for the people living below. One of the results of research in thermal comfort was that our skin is actually very sensitive to radiant temperatures. Even more, it's more sensitive to conduction. It is the most sensitive to radiant temperatures. So having cool surfaces surrounding your body is perhaps the most effective way of feeling comfort. If the surface needs to be warmer than the body in cold temperatures, cold climates, so be it. If it needs to be cooler than the body in the case of hot climates, so be it. But using radiant temperatures of surrounding surfaces is a very, very effective and energy efficient strategy. And now, of course, a building like this is designed for different seasons. There are times when you may actually open the window in the pleasant season to let the air through. And during the other seasons, when you close the windows, you also have fresh air which is provided into the building. And during the humid season, that fresh air is especially desiccated so that no additional humidity enters the building to reduce your comfort levels. And in this residential building, a similar principle is used, except that the cooling, I mean, the integration is there about, there's a roof garden, there are shading systems, the walls are insulated, all of that is there. But in additional cooling system, there's a pool of water at the bottom. And this pool of water is then cooled down by a fountain so that the temperature of the water comes close to wet bulb temperature. This wet bulb temperature is then, the water at wet bulb temperature is then pumped through the floor slabs to take away the heat from the floor slabs. A relatively low-cost method of giving a degree of comfort as compared to an air conditioning system which is dependent on a highly energy-consuming refrigerant cycle. This is how it is laid out in the floor slab. Pipes run through the floor slab and they're connected to pumps that run the water through the pool, the cool pool at the bottom of the courtyard. And the courtyard itself is a vertical garden. So, there's another way of keeping the outside cool, microclimate design. And traditionally, if you look at buildings in your part of the country, old buildings which are considered to be really well built and very comfortable, you'll see that the use of thermal mass and controlled ventilation were the two essential strategies that were being deployed all the time. On the top, we have Padmanabhapuram in Kerala, where you have these deep overhangs where the sun can simply not enter the internal space. It's always reflected light that's coming in, soft reflected light that's coming in. Sun can't enter directly, right? And the upper structure is lightweight, but the slabs in the lower floor are heavy. Okay, so you get a certain benefit of a flywheel effect, and you get the best of air movement because of high humidity. The bottom example is from Jaisalmer, totally different climate, hot, burning desert climate, very dry. Once again, very heavy thermal mass, and it is in this climate that you get the basement put to use. So there's a basement in this big Haveli, and on the outer face, you have a second layer outside the external wall of the building. The second layer is the Jharokha layer, where the perforated screens with small windows are placed. Okay, so this is in a way following the same principle that I was showing in a low-cost housing project earlier. External screen, perforated, lightweight, through which the air can pass to cut out the sun. And this is just a fun project where we talk about heat sinks. This is a small house built into a sand dune. The oval shape that you see is a python. It is a rain collector. And the circular shape that you see in the middle is a well. So the rain collector collects the rain, which rains 3 times for a few hours during the entire year, collects the rainwater and puts it into the well in the center. And the rooms of this house are just spanning across, buried into the ground, across the across the well. So the contact with the ground, where below a certain depth, say below 3 meters or so, or 4 meters or so, the ground temperature hardly varies through the year. You'll find that the ground temperature is roughly the annual average temperature, which is reasonably comfortable. So it's just like, you know, if you're a mouse, you burrow into the ground and you live there. So it's a little bit like that. So that's one kind of using a heat sink of the ground through ground coupling or ground contact of the building itself. And then there's a roof terrace. So you can come to the roof terrace. This roof terrace is also shaded, by the way. And during the winter months, the leaves fall off and the leaves on the vine fall off. And during the summer months, you grow tori and you grow other vegetables that give you shade on the roof. So in the summer months, you can come out and sleep on the roof terrace. And in the winter months, you can catch the sun to heat up the roof during the daytime. So an example of how architectural design actually does quite a lot as a response to the climate. Here's the building, and you can get the feel of earth coupling here. And then, of course, exposure to the night sky also. Just to end, something from Iran. And this was a technology that was developed hundreds of years ago through lots of experimentation and very good building science, very good building science. So you have in this section of the house, which is shown as a diagram, you have a wind tower, which catches the wind from the windward direction. And this wind moves into the cool basement. And then the wind is pushed because of the movement, the negative pressure on the exhaust side. The wind enters the rooms, circulates, and then exits on the exhaust side. And in that process, it pulls up more cool air from an underground water channel that is connected to the canals, which is amazing. So you get cool air flowing over the water. As the water evaporates, it cools the air above it. This air is pulled into the basement by natural wind currents and cools the basement down. So what could be more climate responsive than this amazing building? So you can call this an engine that uses climatic factors. Thank you very much. If there are any questions, please come up with the questions now, or you can post your questions, they can be answered later.
So, good morning, Mr. Lal.
Good morning.
My name is Ghanshyam Pal, and I'm calling from Shivnathar University. I have a question, sir. The examples you have cited, they all have high thermal masses, whereas high thermal masses are, they tend to be uneconomical in the modern building design. So, how do you balance these?
Well,
thank you, sir.
Yes, yeah, that's a very, very good point. By and large, in the northern part of our country and in the central parts of the country, where traditionally we built with heavy materials, right? As we progress into contemporary construction techniques, the mass of buildings is coming down. Okay, no doubt about it. And because of the amount of material that is consumed in heavy mass buildings, and because of the economy of space that we are looking for, we also want to reduce the mass of the building. However, every building has elements of mass in it. The flooring system, most building types still have a fairly heavy mass. Okay? So consider the floor slabs of the building as the thermal, the things that give you the thermal inertia. Okay? And consider the external envelope of the building as belonging in two layers. One layer on the inside, which can be a thin brick wall or a hollow concrete wall, relatively less mass, but with insulation on the outside. Or a wall system, which is a medium weight, lightweight insulating material like lightweight concrete or a hollow clay block. Okay. So you get a combination of an envelope which resists the flow of heat. In that envelope, the inner surface may have some more mass. I'm just looking at it from the from the physics point of view. Inner surface has some mass, outer surface is the insulating material. And then you have the slabs as the main thermal flywheels, right? Even with this, we are finding that we are able to do quite a lot in terms of thermal comfort. Surely you cannot get the same degree of thermal constancy that you would get inside the Taj Mahal, right? You will not get that. But still, it does go a long way. So this actually now brings us back to the role of our, say, building engineers, electromechanical engineers, and architectural designers. With the availability of materials today with different properties, considering the needs for economy of space and also economizing on the consumption of material, we still have to use the same principles of building physics to find the optimal solution. So it comes back to actually very good calculated design. Now we have luckily excellent simulation tools with which you can optimize the design potential.
Thank you, Mr. Lal. Thank you.
Mr. Lal.
Yeah.
Very good morning and thank you for such a nice presentation. I have one question. You have shown the potential of radiant cooling. So our Indian buildings are ready to having these active systems, because there are a lot of problems as of related to the radiant coolings. So what are your perspective in modern Indian buildings for this active system?
Well, the radiant cooling system of the type that I showed you just now came into practice roughly 10, 12 years ago in India. Okay?
Right.
This was a technology that was developed in Europe, and they hadn't developed for cooling buildings. They developed for heating buildings, believe it or not, at one time. But some companies were able to work out the engineering of it, the type of piping, the circuitry of piping, the thermodynamics of what the piping can do when it is embedded in concrete, how much, at what rate, by how much flow water, at what rate it can absorb heat and transfer heat, etc. And of course, the material of the pipe itself is the crucial thing. And techniques of repairing the piping in case there is damage to it and there's leakage. And techniques of laying the piping in a particular manner so that if you have to, let us say, you have to abandon one circuit, maybe you can abandon one circuit, but keep the rest of it. So over the years now, over the last decade, this technology has evolved. Many buildings and contractors have installed this system, and it is being found to be extremely efficient. There are variants to this. embedded cooling, radiant cooling system. There are variants where the radiant panel is like an exposed panel. It's like, we have electric heaters, the radiant electrical heaters. It's like a radiant cooling panel, which can be suspended above where your people are sitting in the ceiling space, and cool water is then run through it. There's another variant of the same thing. It has its own pros and cons. So once again, I should say, let's think of the principle. Let's study the technologies that are available. And let us understand that it's actually giving you a very good return for your money. Great efficiency. There's extra investment involved at the beginning, but over the long run, it pays back very well and gives you a very good, the type of comfort that you get with radiant cooling is physically somehow much better. I mean, this is the report. Wherever we have done radiant cooling in 3 projects now, the report from the occupants is that they say, oh gosh, it feels so nice, but where is the air conditioning? They say, where is the air conditioning? It feels so nice. And they say it feels nicer than other kinds of air conditioned spaces because radiant cooling is really a very comfortable form of cooling. But it's coming in and people are learning how to put it in.
Right. Thank you for the answer.
Well, the reason why I showed you this radiant cooling system was the potential of what I call integrated design. That the thermal mass of the building, its external walls, their properties, and the windows, etc., along with the electromechanical systems can be integrated into for better optimization. Supposing I was designing the air conditioning system as if there was no thermal mass at all, I would design it very differently. But if I'm designing the air conditioning system to take advantage of thermal mass, take advantage of the radiant potential of thermal mass, then I'll design the air conditioning system differently, won't I? So it's really to bring that out.
Right, sir. You already mentioned that it is catering the radiant load, so it is very effective, I think.
Yeah. The sensible load it takes care of mostly. Okay, thank you all very much. Back to you, Udayji.
Thank you, Lal sir, for a nice and informative session. So we'll move on and we'll start the next session now.
Stop share.
So I hope my slides are visible.
Yeah.
Okay. Okay, good morning, everybody. The next section, we are going to talk about the energy efficient building, the role of thermal comfort and building heat transfer. So we are broadly going to talk about the thermal comfort, how it is defined, and what are the challenges and the solutions which are available. And then we will briefly talk about building heat transfer and various heat exchange and internal heat gains within the building. So as we know that most of us spend a significant amount of time indoor, and this indoor environment quality is therefore a very important parameter which affects health and comfort of building occupants. Where so in this IEQ, this thermal environment plays a major role and thermal comfort plays a major role. So thermal comfort is basically defined as the condition of mind which expresses satisfaction with the surrounding thermal environment. So basically it is used in relation with how warm and cold a person feels when it is subjected to a certain environment. So it is nothing but basically the heat balance, the amount of heat which is produced within the body, or the amount of heat transfer to the body, and amount of heat lost by the body. So it is basically the balance of these two. So whenever there is a balance of this heat produced in the body and heat lost by the body, so our body remains in thermal equilibrium. And whenever we have such thermal equilibrium, we try to attain or we achieve the thermal comfort. And there are other conditions also when we say that a person is feeling thermally comfortable. So under this, under the condition of this thermal comfort, so the mean skin temperature and also the body sweating should be within the comfortable limit. So for mean skin, it is skin temperature, it is usually close to 32 to 34 degrees Celsius. And there should not be any local discomfort at any body part. So if all these conditions are satisfied, we say that a person is feeling thermally comfortable. So if you talk about the heat balance mathematically, so there are various modes of heat transfer which are involved here, right? So there is a heat which is produced within the body because of metabolism, and then there are heat exchange and heat lost by the body. So if we talk about the heat which is, or the energy which is lost from the body, it involves the external mechanical work, also the evaporation heat loss. So that is why if you see here the equation, so this S denotes basically the amount of heat which is stored within the body, right? So which is equal to the amount of heat produced minus the amount of heat lost. So M here is basically the metabolic heat production, and this W denotes the external mechanical work, which is again the energy which is lost, and then E, capital E, denotes the evaporation heat loss due to sweating and perspiration. And if you see the other terms like R, C, K, so basically these denotes the radiation exchange, convection, and the conduction heat transfer, right? So now these mode of heat transfer, conduction, convection, and radiation. So body can exchange heat, either it can gain heat or it can loss heat depending upon the external environment temperature, right? If the environmental temperature is higher, so obviously body is going to gain heat because of all these three modes of heat transfer. Similarly, again, it depends, this heat exchange due to respiration can also be positive or negative depending upon the condition. So now this amount of heat which is stored in the body, which is denoted here as S, now it governs whether your body core temperature is going to increase or decrease, right? So if it is very hot outside, so probably this S is going to be positive, right? So it will increase your core temperature and it will lead to uncomfortable situation, or probably people will start feeling hot or warm. Now, so these modes which we talked about, conduction, convection, and radiations, now it can be either heat can flow through these modes of heat transfer, either outside or inside the body, right? Depending upon the external environment temperature. But if you see here, this perspiration heat loss or the evaporation heat loss is always going out from the body. So, and in fact, this plays a very important role in the warm or hot environment, because that is one of the effective mechanisms which we have to lose heat if the environmental temperature is higher than the body temperature. So, and all of us know that our body is meant to operate within a certain temperature range, right? Means our body core temperature should be around 36.5 to 37.5. So our body tries to maintain this temperature between 36.5 and 37.5 under normal circumstances. But we know that the outdoor environment temperature is can vary significantly, right? It can vary from, let's say, 0 degrees Celsius or minus 5 degrees Celsius to 45 degrees Celsius. So in order to cope up with this variation of the temperature or the surrounding temperature, so our body has the thermal regulation system. So let's talk about this thermal regulation system and the mechanism which we have within the body to manage this significant change in the environment temperature. Okay, so let's talk about the cold environment first. Let's say if the surrounding is very cold. So our body basically, the first mechanism which we have in order to cope up with this low environment temperature is the vasoconstriction. So our body, so the artery basically constricts. So the heat, so the blood flow through artery reduces, and that way it tries to maintain the body heat within the body, right? Because what happens is that these arteries are basically passing through means close to epidermis, and then the hot blood loses heat to the surrounding, right? So by reducing the flow rate of the blood through artery, we try to minimize this loss of heat from the blood from the body to the surrounding. So this is one of the mechanism which is there in our body or in our thermal regulation system, which tries to maintain the core temperature, or which tries to keep ourselves comfortable. Now, then we have other mechanism. Let's say if it is too cold outside, so we have other mechanism like shivering and the goosebumps, which we observe sometimes. So this tries to create a layer of air around our body. So and you know that air is a good insulating material. So that way it avoids or restricts the heat transfer from body to the surrounding. So that way we are able to maintain the, we try to minimize the value of S, or the storage of heat goes towards the negative side, right? And then we have shivering also as one of the mechanism where there is a heat production, additional heat production because of the friction between the muscles. So in case of shivering, the lot of heat is generated within the muscle tissues. So that way, somehow we try to achieve the heat storage within the body somewhere close to zero, and avoid it going to be negative. Similarly, in case of hot environment, again we have some defense mechanism in our body. The one which we so like we discussed earlier, the vasoconstriction. So the opposite of it is vasodilation. So if the outdoor temperature is very high, so and then most of the heat transfer mechanism like conduction, convection, and radiation acts in an opposite fashion, where means they try with all these mechanisms, we gain the heat from the surrounding because the surrounding temperature is higher than the body temperature. So in that case, the vasodilation happens. So our artery basically becomes dilated, and the mass flow rate, the blood flow rate increases through artery, and that way we try to lose additional heat from the body to the surrounding. And then the most effective mechanism which we have to deal with hot environment is the sweating. So we know that it is a latent heat. Sweat evaporation is going to remove the latent part of the heat. So, and we know that it's significantly higher compared to the sensible part. So obviously a lot of heat can be removed with the help of sweating. So after talking about this thermal regulation system, now let's see on what factors this thermal comfort depends, right? So it majorly depends on 6 factors, which can be classified as personal and environmental factors, right? Environmental factors involve temperature, humidity, mean radiant temperature, and the air velocity. And the personal factors involve the metabolic activity or the physical activity of the person, and also the clothing, right? So by properly managing all these 6 parameters, so thermal comfort can be maintained, right? So, and it depends on all these 6 factors simultaneously. And this thermal comfort, again, as I said earlier, under thermal neutral conditions, so this S value, or the storage, body heat storage, is going to be somewhere close to 0, right? So by, let's say, by wearing additional clothing during winter, we somehow try to reduce these losses by conduction, convection, radiation, right? And then somehow we try to maintain the balance between the metabolic activity and the heat loss from the body, so that this body heat storage is not negative, right? It is somewhere close to zero, so that we can maintain the thermal comfort. Now, thermal comfort is usually denoted in terms of one of the factor or one of the parameter and to denote the thermal comfort is the predicted mean mode PMV, right? So it basically gives the subjective ratings of a group of people in a particular environment, right? And it depends on the metabolic rate and the latent heat load of the body, which is nothing but again the energy balance or the heat balance. And this also gives us another very important factor known as PPD, percentage of people dissatisfied. So how many number of people are dissatisfied. So this PMV, you can see here that PMV is equal to 0 denotes the neutral condition, thermoneutral conditions. And the moment this PMV goes, the PMV value goes above 0, so people are either feeling warm or hot. And if it is negative, so it means either people feeling cool or cold. So either way, once we deviate from 0, so we'll feel uncomfortable. We'll start feeling uncomfortable. So, so in order to maintain the thermal comfort, or in order to achieve the thermal comfort, this PMV value should be somewhere close to 0. And it has been noticed that the PMV value between minus 0.5 and 0.5, it results in a situation where almost 90% population is satisfied. So in general, the design is considered, the HVAC design or the building design is considered good if almost 80% or 90% population is satisfied, because we cannot satisfy 100% population or the occupants. And thermal comfort, now again, this is the thermal comfort zone. So you can see here that for two different velocities, air velocity, right, means the thermal comfort zones are marked in this psychometric chart. So you can see here that as the air velocity increases from 0.1 to 0.5 meter per second, so we will feel comfortable even at higher operative temperature also, right? So this is what happens when we even at, so it tells us that even if temperature is higher, just by switching on the ceiling fan, we may feel comfortable, right? We can achieve thermal comfort. Sorry. So this is the effect of one such parameter, and means this thermal comfort zone, it actually shifts towards the left side if you go for higher clothing or higher flow value of the clothing, or if you are talking about higher metabolic activity or higher radiant temperature. So now what happens when you increase the metabolic rate, right? You will produce more amount of heat, right? So it means your body is supposed to lose large amount of heat. So in order to extract the body heat, which is higher in this case because of higher metabolic activity, so the outdoor temperature or the outside temperature should be lower, right? So it means you will feel comfortable at lower temperature. So that is why your comfort zone is going to shift towards the left side in case of higher metabolic activity, and similarly for higher flow values or higher radiant temperature also. And if you see the other side of the story, so the comfort zone basically shifts towards right if we go for lower metabolic rate or lower metabolic activity or lower physical activity, right? Because now your body is producing lower amount of heat, right? So you don't have to release so much body heat in order to be in a thermoneutral condition, right? So it means you will feel comfortable even at higher operative temperature also. Just a second. Yeah. So So why thermal comfort is necessary? So it is necessary not only for the satisfaction, but it also affect the efficiency or the work efficiency or of the occupants. So here is an example of telegraph key operator study conducted by NASA. So we can see here that as the ambient temperature or the surrounding temperature increases, the number of strokes per hour also increases, right, for the telegraph key operator. So it tells us that your surrounding temperature or the thermal comfort of the occupants is going to govern the work efficiency of the occupants also. And there are a lot of studies have been conducted on this, where people are actually analyzing the effect of thermal comfort on the productivity loss. So and there are a lot of interesting results which are there in the open domain. So which one such example is given here, where uh, one such study has considered that over a period of 10 years, the productivity loss is equivalent to one year's salary, right? And if you maintain the your work environment temperature 2 degrees difference compared to the thermoneutral conditions, so so it is going to have the productivity loss, which is going to be 2.5 to 5 times higher than the cost of the HVAC system over the entire life cycle. So basically, there are studies which says that the productivity loss can be even higher than running the or installing the HVAC system over the complete life cycle. So in that sense, thermal comfort is important, and as we saw earlier that nowadays we are using a lot of active systems to maintain thermal comfort or to maintain the surrounding temperature or the indoor temperature, and obviously the other parameters like humidity and air velocity, right? So and there are some positive aspects of these active systems and some negative aspect of it. Obviously, when we utilize or deploy these active systems, so thermal comfort and indoor air quality improves, right? People become, your productivity will improve, and there are so many other advantages. But at the same time, the energy consumption is going to increase. The building energy consumption is going to increase, and at the same time, these active systems, most of the time they use refrigerant, right? So it can cause greenhouse gas emissions issues. Now, as far as Indian scenario is concerned, I think it is already discussed by the first speaker, right? So what is the scenario right now? So building usually consumes around 33% of, or around 30% of the energy, right? And most of this energy is utilized for by the active system to maintain the thermal comfort, right? So, and as Mr. Prasad was talking about, so there are a lot of buildings which are supposed to be built over next 30-40 years, right? And in that sense, the energy consumption is going to be significantly higher in the near future. So now, in order to reduce this potential increase in the building energy consumption, right? So what are the solutions? So the solution could be that, and obviously the greenhouse gas emissions issue is also there. So what are the possible solutions? So the possible solution could be that we rely on the energy efficient building, or we go for sustainable HVAC systems, right? So let's focus on the energy efficient building as the today's topic is more relevant to this. So when we talk about energy efficient buildings, so there are various aspects to it, right? Climate responsive building design is one of them. So Lal sir was talking about it. And then we also talk about climate responsive cooling system design. So you should have energy efficient appliances, you should have smart appliances, right? Which can basically respond to the change in climate, okay, in order to reduce the building energy consumption. Similarly, one of the major factor which governs or which can which hinders the making the building energy efficient is the behavior of the building occupants, right? So how they adapt to the change in the environment. So this is one of the important factor which is responsible or which helps in making energy efficient buildings. So if you talk about this set point temperature, right? This is one of the point which is most of the time governed by the building occupants and their behavior, right? So we should set, or we should opt for a set point temperature which can still give you thermal comfort, or let's say we can set even higher set point temperature by just switching on the fan. So this is one such example, right? And then there are a lot of building codes nowadays, as Lalji was talking about, that there are ECBC for commercial building, there is a Eco-Nivas Sanhita for residential building. So they talk about different aspects, like what should be the U value of wall, right? What should be the U value and other things, right? What should be the SHGC value? So these codes also specify certain parameters in order to make the building energy efficient or sustainable, right? And one more very important factor which helps in making building energy efficient is to reduce the cooling or heating load of the building. And as far as India is concerned, we usually concerned about the cooling load of the building, and there are various passive strategies which are available, which can be utilized to reduce the cooling load of the building, right? So it can be a natural ventilation, it can be a green roof or the cool roof, or it can be BIPV, it can be designing your envelope properly, which involves your wall, roofs and windows. And then it can means you can have other architectural interventions to reduce the cooling load, like orientation. In the last session, you saw how the orientation plays a major role and how we decide how the building should be oriented. And if it has to be oriented east-west, so what all options we have. Now, so in this particular session, we will be focusing mainly on the building heat transfer and its quantification. So how to quantify the heat transfer through building envelope, and also what are the various parameters which plays major role there. Okay, and what are the we'll try to define those parameters and see how they affect the building heat transfer. So as far as building cooling load is concerned, so it is basically the load which is to be this much amount of heat is to be extracted by your active system. Say for example, if you're using an active system, right? So this cooling load is basically the heat which is increased inside the building, right? Because you are outside, let's say if you're talking about cooling load, so outdoor it's let's say hot environment. So obviously the heat from outside will come inside the building, right? And there are various ways by which this outdoor heat or outside heat can come inside, right? It can be due to conduction through envelope, which involves your wall, roofs and windows. It can be through convection mode of heat transfer with the help of ventilation or the infiltration in your building, or it can be solar heat gain through window openings or windows. And then within the building also you can have certain equipment or occupants that also contributes to the internal heat gain. And out of all this, the heat transfer from outdoor to indoor, or the building cooling load, the major contributor in the building cooling load is your windows and roof. So these two are the significant contributor as far as the cooling load is concerned. So let's see the building heat transfer and different modes of heat transfer which are there. So as we know that buildings act as a barrier between us and the external environment, right? So now, whatever heat was supposed to fall on us directly will be absorbed by the building, and subsequently the building will release it to the external environment as well as indoor, right? So that way the heat which is means is anyway going to come inside, right? In this case, through the building envelope. So now what are the external heat exchanges associated with the building? So we can have conduction heat transfer through walls, through roofs, right? We can have the shortwave radiation which is coming inside through windows, right? And whatever heat is absorbed in your building envelope, which involves wall and roof, because of which the envelope temperature will increase, and because of its temperature, now we know that this can actually emit radiation, and this is going to be the long wave radiation, right? So and then obviously you can have convection heat transfer and the ventilation through window openings. So we see that the external heat comes inside via the building envelope by various modes of heat transfer, right? And all this heat which is coming inside contributes to the building cooling. So if we can somehow reduce this heat transfer inside through the envelope, we will be able to reduce the building cooling load. And this will not only reduce the energy consumption or the load of the active systems or the requirement of the active system, but it will also maintain the thermal comfort probably without use of active system or with least possible energy consumption. And then you have the internal heat gains, which involves the heat gain from the occupants, artificial lighting, and the equipment or the appliances which we use inside. Right. So let's talk about the occupant first. So the heat gain from the occupant or the internal heat gain from the occupants can be a sensible heat gain or the latent heat gain. Right. So we have this kind of table or the data available from ASHRAE, which gives us the indoor heat gain by or the internal heat gain by the occupants at different activity levels. So you can see that as the activity level increases, so the internal heat gain from the occupant also increases, right? So and it basically involves both sensible component as well as latent component. Say for example, if we talk about a person who is seated, right? So the total heat gain on internal heat gain from the person is going to be 105 watt, and significant part of it, approximately 7 watt, is contributed by the sensible heat gain, and the rest is latent heat gain, right? So that way, depending upon the number of occupants, depending upon the activity level of the occupants, we can actually find out how much is the internal heat gain contributed by the occupants, right? So that way we can quantify this internal heat gain by occupants. Similarly, we have a lot of equipment and appliances also which we use. So the internal heat gains by these appliances, again, this data is available from ASHRAE, right? So depending upon the equipment which we use, it contributes different amount of internal heat gain within the building, right? And this data can be taken from a standard. The third internal heat gain, or the third component of the internal heat gain, is the artificial lighting, right? So depending upon the wattage of the lighting, artificial lighting, right, it also contributes to the internal heat gain. So you can see here that it can be obtained from this particular formula, where W is the total light wattage of the artificial lighting which we use. Then FUL is the lighting use factor, which is usually 1, and FSA is basically the special allowance factor, right? So depending upon the type of lighting which you use, its value can be either 1.2 or 1, right? If you are using fluorescent light, it is typically taken as 1.2, and if you are using incandescent light, so it is typically 1, because in this case there is no ballast, right? So obviously the internal heat gain in case of this incandescent light is going to be lower because of the absence of ballast. So this is the way we quantify, or we can actually calculate how much is the internal heat gain through various components, right? So that means if you want to calculate the total cooling load of a building, so now you know how to calculate the internal heat gains, right? Then there are other methods also to calculate internal heat gains due to artificial lighting. One such method is the lighting power density, right? So it is basically the heat gain per unit floor area, right? So again, this LPD, which is the lighting power density, is given in the standard, right? And you can take it from there depending upon the uses. In the ASTRE standard, it is given in this particular form, but in the ECBC, it is given either in terms of the building types or the use of building. What is the use of this particular area? So accordingly, we will have different lighting arrangement and we will have different heat gain because of the artificial lighting. Now, depending upon the either the type of building or the space or the function of the building. Right. So after the internal heat gain, let's see the heat exchange through wall and roof first. Right. So as we saw earlier that whatever heat, external heat we have, so either it is absorbed by the wall or the roofs, and then its temperature increases. Like let's start it from the beginning. So let's say you have a roof and a wall. Okay, you can focus on the right side. So let's say you have a roof and a wall, right? And solar radiation is falling on the roof and wall, right? A part of this solar radiation falling on the roof and the wall is reflected back depending upon the reflectivity of the surface, right? And part of it is going to be absorbed by the roof and wall, because of which its temperature will increase. And because of its temperature, you know that every body which is at a temperature higher than 0 Kelvin, it radiates, right? And so it radiates toward the outer side. So that way it releases heat to the surrounding. So if we talk about the heat transfer from the wall or roof towards the outside, it is either in terms of reflection or the emission, right? So there is a factor which, or there is a parameter or the property which plays a significant role there, and we call it solar reflective index of the surface. It can be the solar reflective index of the roof surface or the wall surface, right? And part of this heat means once it is reflected, so part of it is will come toward the inner side or toward the inner surface through conduction, and part of it is going to be absorbed in the wall or roof, right? Now, if you talk about this wall and roof, so whatever heat passes through this means, you know that the outer surface temperature is going to be higher, right? Because it absorbs the solar radiation, and the inner surface temperature is relatively lower. So basically there will be a conduction heat transfer from through this wall or roof towards the inner side, right? So the amount of heat which is getting transferred or which is getting conducted from outer surface to the inner surface through the wall or roof is going to be governed by the thermal transmittance of the wall or roof, right? And there is another important factor that apart from this conduction heat transfer, there will be some heat which will be absorbed in the structure or the envelope, right? So so the thermal mass of the roof and wall also plays a role. So out of this, the entire thing, we saw that when we talk about the heat exchange through wall and roof, so there are three properties which plays a major role, right? So what are those? So it is basically the previous slide, we saw that it is solar reflective index, right? Which talks about, which basically takes into account the reflected part and the emitted part towards the outer side. And then we have this thermal transmittance and thermal mass of the wall and roof assembly, right? So these are the three important parameters when we talk about the heat exchange through wall and roof. And depending upon the value of these parameters, you will have more either higher heat transfer towards the inner side or the lower heat transfer. So basically by properly controlling and properly understanding these values, we can actually control the building cooling load through envelope. And once the heat reaches toward the inner side of the envelope or the wall and roof, now you will have either convection heat transfer and radiation heat transfer. Now, if you have higher heat transfer through the building envelope, right, by conduction from outer surface to the inner surface, so what will happen? So the inner surface temperature of the wall and roof are going to be higher, right? And if the inner surface temperature is going to be higher, so let's say if there is an occupant who is standing somewhere inside, right? So you know that there will be some surface temperature of the occupant, or you can say the skin temperature of the occupant, and there is some temperature of the inner surface of roof and wall, right? Now, you know that there will be a radiation heat exchange between the inner surface of wall and roof and the occupant, right? So if the inner surface temperature is higher, so you will have higher radiation heat transfer from the inner surface of the wall and roof to the building occupant, right? So that is what we do. In case of radiant cooling, we try to maintain this inner surface temperature somewhere lower, right? So that instead of gaining heat from the inner surface of wall and roof by the occupant, we lose heat to the inner surface of wall by maintaining the inner surface at a lower temperature. So that way it is a very efficient and effective mechanism by which you can significantly reduce the energy consumption also, and you can actually enhance the thermal comfort also. Okay, so let's talk about these three properties which we discussed, which plays a major role as far as heat transfer or the heat exchange through wall and roof is concerned. So first is the solar reflective index. So it is a measure of solar reflectance and emissivity of the material. So we know that whenever solar radiation falls on a surface, so part of it is reflected and part of it is transmitted if it is a transparent, semi-transparent surface. But since we are talking about wall and roof, so there won't be any transmission as such, right? So what happens is that in this case, in case of wall and roof, whatever solar radiation falls on the surface, part of it is reflected and part of it is absorbed, and which is emitted later because of the increase in the temperature. So when we say that, so when we talk about the heat exchange through wall and roof toward the outer surface, so this property, solar reflective index, plays a major role, right? So it basically takes into account the reflectance as well as emittance of the surface, usually the outer surface, right? So so basically, if you see here, there are two standard surfaces which are defined and their SRI value is defined. So if you talk about a standard black surface, so it will have a reflectance of 0.05 and emittance of 0.9. So if there is a surface having reflectance 0.05 and emittance 0.9, so we assign it SRI is equal to 0, right? Similarly, there is another surface which is defined standard white surface. So for this, the reflectance is 0.8 and emittance is again 0.9. So this is assigned an SRI value of 100, right? So now if you see here, as the SRI value increases, right? So let's say, for example, standard white surface. So SRI value is higher, obviously it's 100, right? So for this, reflectance is higher. So it means that a material having higher SRI value is going to reflect more, right? So whatever heat is coming to the surface, most of it, or at least 80% of it, is going to be reflected back, right? So in that sense, it will reject a significant part of heat which was supposed to come inside, right? So it means if your SRI value is higher, right, so it is better, okay? And if your SRI value is lower, it means it is going to reflect lesser amount of heat and it is going to absorb a significant amount of heat. And since it is absorbing a significant part of the heat, so your surface temperatures are going to be higher, And obviously, if surface temperature is higher, again, the heat exchange with the occupant by radiation mode is going to be higher, right? So it means your cooling load will increase or the occupants will not feel comfortable, right? So higher SRI value is preferred in that sense. Okay, so you can see here one example, the standard black surface, right? It means the SRI value is equal to 0. So you can see that the surface temperature in this case is 60 to 70 degrees Celsius, whereas for the white roof with SRI value 100, the surface temperature is somewhere close to 40-45 degrees Celsius for the same environmental condition. Okay, for the same ambient air temperature 37 degrees Celsius. So you can see there is a huge difference of around 15 to 20 degrees Celsius, right? But just by changing the SRI value of the roof material. So obviously it will have a significant effect on the cooling load also. Now, nowadays, even the standards also specify the minimum requirement in terms of either the reflectivity or the emissivity, or they talk in terms of the SRI value, right? Okay, so these are some of the high SRI products. So which involves the roof tiles or paints or the China mosaic finish, right? So all these material has higher SRI value. So it means that these, if you apply these material over your roof, so it is going to reflect a significant part of the heat, and your surface temperature is going to be lower, or your building cooling load is going to be lower. Right. So higher SRI means lower surface temperature. So obviously lesser amount of heat ingress inside during the daytime. Okay. So this was the first property, right? The second important property is the thermal transmittance. But before going to the thermal transmittance, let's talk about the thermal conductivity first. I think most of us know what do we mean by thermal conductivity. So per unit temperature difference, how much heat is going inside, right, or passing through an object, is basically the thermal conductivity. So here in this particular table, the thermal conductivity value of some building material which are typically used is shown. So you can see here that say for example the dense concrete, reinforced RCC, clay brick, etc. So, and also the fly ash brick, so, and AAC block. So you can see here that for most of the building material or volume material, so the thermal conductivity ranges somewhere close to 0.6 to 1 watt per meter Kelvin, right? Obviously the AAC block is an exception because it has significantly lower thermal conductivity. So it means if you instead of using normal clay brick, if you go for AAC block, it is going to reduce the heat transfer through the envelope, right? And then you have some insulation materials also for which conductivity is going to be of the order of 10 to the power minus 2. And these insulation materials are also used nowadays for building construction. Now, coming to the thermal transmittance, so we nowadays see that our building walls or the roof is not a single layer arrangement, right? It involves, or it consists of multiple layers of different materials, right? Say for example, in this case, you have a brick walls, 2 layer of brick walls, and in between you have insulation, right? So it's a multi-layer arrangement usually, be it your wall or roof, right? So in that case, we define something known as thermal transmittance, so which is nothing but the inverse of the summation of the thermal resistances. So it takes into account the convection resistances towards the inner side of the wall and also the convection resistance towards the outer surface. So which is shown here from in terms of RSI and RSE, right? And then it also involves the thermal resistance offered by different layers, right? Say for example, 2 brick layer and 1 thermal insulation layer, right? So in that sense, it is the inverse of the total thermal resistance offered by the wall. So it means that higher U values will indicate lower thermal resistance, right? Or you can say the higher U value means you will have more heat transfer through the wall or through roof, right? So we should try to maintain the U value as low as possible. Right. So here just in comparison is shown depending upon the thermal conductivity of material, what is going to be the thickness of different materials. Say for example, since the RCC has higher thermal conductivity, right? So for a same value of U, which is 0.4 watt per meter square in this case, you will have to deploy thick 3.7 meter thick RCC block in order to get this much amount of thermal resistance or this much amount of U value. So you have wide range of building materials available, and you know that means even nowadays the standards, like as I was talking about it earlier, even the ECBC or the Econivas Sanhita talks about a minimum U value for wall as well as for roof, right? So you have a lot of options in terms of building materials. So depending upon the requirement, or depending upon the requirement of U value, you can select a suitable building material, or probably the multiple layers of the building materials. Okay, so the third important property is the thermal mass, right? All of us know that it is basically the ability of the material to store heat, right? So higher thermal mass indicates that material can store more amount of heat, right? Say for example, in this particular table, the volumetric heat capacity of different building materials are given, right? So we can see here that RCC and clay bricks generally have higher heat capacity, so they can store more amount of heat inside. And on the other hand, if you see the insulation, they have significantly lower heat capacity. Okay, and AC is again a good option in terms of if you want to minimize the energy storage, right? So you can go for AC block because it has another advantage, that its conductivity is also lower, significantly lower compared to clay brick or RCC. Right. So and when we talk about thermal mass, so it is inherently the transient process, right? So so usually what happens is that when we talk about steady state, right? So the U value is an important parameter, because under steady state, if you change the U value, you will have different heat transfer rate depending upon the U value, right? But in actual scenario, there is no steady state, right? The temperature varies throughout the day, right? Morning temperature is something else, and then throughout the day it increases and then decreases, right? So it's the outdoor environment is basically the temperature is changing. So it's a transient process or unsteady process. So in that sense, the U value is not going to be the only parameter which is going to affect the heat exchange or the heat transfer through the building envelope or your wall or roof. So, so when we talk about this unsteady process, so the thermal mass or the heat capacity of the building materials comes into the picture. Okay, so say for example, in this case, whatever heat comes, right, some amount of heat comes, falls at the outer surface of the wall, right? So part of it is absorbed by the building material or the wall, right, and rest goes away or goes forward. So in that sense, within this building material, because of its thermal capacity, a significant portion of the heat is stored, right? Only a part of it goes inside or the inner side. So obviously the temperature at a particular time instant is going to be different at the outer surface of the wall and the inner surface of the wall. And obviously the outer surface temperature is going to be higher compared to the inner surface temperature. So if you see the typical variation of temperature versus time for the inner and the outer surface of the wall, so you will see this kind of variation. So sorry, this orange line basically indicates the outer surface temperature, how it varies with respect to time, right? And this the other line, it basically shows the inner surface temperature variation with respect to time. So you can see that when the outside surface temperature is maximum, right, or highest, so the inner surface temperature is not highest, right? There is some lag. Okay, so let's say so the outer surface temperature is maximum at 3 p.m. whereas the inner surface temperature is maximum somewhere in the midnight, right? So there is a lag when this temperature becomes maximum at the inner surface and outer surface, right? So this time, this is defined as the time lag, right? The difference between the two times when the surface temperatures are maximum or peak or at the peak of the inner surface and outer surface temperature. And also you can notice from this particular graph that the extent of the peak temperature of the inner surface and the outer surface. So this is the magnitude of the outer surface temperature, right? It is significantly higher compared to the peak of the inner surface temperature. So there is a decrement of the peak surface temperature also, if you talk about inner surface and the outer surface. So whatever decrement you have, so that is again another property known as the decrement factor. So since most of the processes, or when we talk about building, so we all means it is always going to be unsteady. So apart from U value or the thermal transmittance, right, we will have another two important parameter which are going to affect the heat transfer under unsteady conditions through wall and roof. And those two parameters are time lag and decrement factor. So we should not only bother about the U value, but we should also bother about the time lag and the decrement factor when we talk about heat transfer through wall and roof, because it is inherently an unsteady problem, right? And we should note that this time lag and decrement factor, its value depends on the U value of the material. It depends on the thermal mass of the material, and it also depends on the climatic condition, right? Okay. So we can summarize this, or we can quantify this, all these modes of heat transfer, right? So we have this conduction heat transfer from outer surface to the inner surface through the material, right? It can be calculated as UA delta T, right? Where delta T is basically the temperature difference between the outer surface minus the inner surface, right? And U value, I think all of us know by now. So it is basically the thermal transmittance, right? And then you also have convection heat transfer, either inner side of the wall or the outer side of the wall, or through from the human body to the surrounding, right? So again, this can be quantified in terms of Newton's law of cooling, which is HA delta T, where H convection is the convective heat transfer coefficient. Now its value depends on the air velocity, right? So if you switch on the fan, so air velocity increases, so obviously the H convection increases, right? So you will have higher convection heat transfer when you switch on the fan. So probably you will feel better, or you will feel comfortable. Okay. And then as we were talking about it earlier, so the radiative heat exchange between the occupant and the inner surface of the roof and wall is going to be obtained with this particular formula, which is sigma multiplied by shape factor multiplied by emissivity of the surface multiplied by area, and T to the power 4 minus, I mean higher temperature to the power 4 minus lower temperature to the power 4, right? So so it significantly depends on the temperature, means fourth power of the temperature. So if your building materials are not good, right, if your U value is not is, let's say, higher, so what will happen? More heat will transfer through the wall and roof. So obviously your inner surface temperatures are going to be higher, right? So it means that there will be a significant transfer of heat from inner surface of the wall or roof to the occupant, right? So people will feel uncomfortable, significantly uncomfortable, because of this higher inner surface temperature, right? So that is why we should try to avoid it, and that is why the radiant cooling also plays a very significant role, or it can provide you thermal comfort in a better way with least or lesser amount of energy consumption. Now, after this heat exchange through wall and roof, let's talk about heat exchange through fenestration. So if you can focus on the left side figure, so let's say you have a window, right? And there is a solar radiation which is incident on the window, and this glass window being a semi-transparent material, right? It's not an opaque material, so it can transmit a significant part of the solar radiation, right? So a part of it, the solar radiation falling on the window, is transmitted, and part of it is reflected, and the remaining is absorbed within this window, right? And as it is absorbing the heat, its temperature will increase, and then it can emit the radiation. Obviously, it is going to be the long wave radiation, and it will emit radiation both outside as well as inside, right? And apart from this, if you, I mean, since it is a solid material, so it will also transfer heat by conduction mode, right, from outside to inner side, because outer surface temperature is going to be higher compared to the inner surface temperature of the window. So you will have a conduction heat transfer through glass for the window. And the frame in which this window is mounted will also have the conduction heat transfer, right, depending upon the material of the frame. You can have aluminum frame, you can have PVC frame, you can have a wood frame. Now, depending upon the material, you will have some heat transfer through frame also. And apart from this, you can also have some leakages around the frame or in the window, near the window, right? So from there, you will have some infiltration also. So this will transfer again heat, let's say the hot air from outside will actually infiltrate inside, right? So that way it will also contribute to the cooling load of the building. And obviously, since this glass is at a higher temperature, so you will have a convection heat transfer also, both inside as well as outside, right? So if we talk about this particular scenario, where you are talking about the conduction heat transfer through the glass because of higher outer surface temperature compared to inner surface temperature, right? So it's a conduction heat transfer. So again, the thermal transmittance value or the U value of the glass is going to play a major role here, right? Similarly, when we talk about the conduction heat transfer through frame, again, the U value of the frame material or the conductivity of the frame material or thermal transmittance of the frame material going to play a role, right? So thermal transmittance of glass and the frame material are two important parameters in this case, whereas in this particular case, being a semi-transparent material, it can transmit part of the solar radiation, it can reflect, it can absorb, and then it can re-emit also, right? So there, so the amount of heat which is transmitted and emitted, right, it is taken into account in one particular parameter known as the solar heat gain coefficient, right? So solar heat gain coefficient of the glass, thermal transmittance of glass, and thermal transmittance of the frame material are the three important parameters which are going to affect heat exchange through fenestration. Okay. Right. So I think this is what is written here. Now let's talk about this one by one. So this solar heat gain coefficient is the first parameter. So it is basically takes, it is defined in such a way that it is basically the ratio of the heat which is transmitted, direct transmission, right? Part of it of the solar radiation which is directly transmitted, right? It takes into account that of that, and plus the secondary heat gain by other mode of heat transfer are also taken into account in this. So it in one sense it basically talks about the overall heat transfer or overall heat gain through window, right? Divided by the incident solar radiation. So out of the total radiation which is falling on the glass, how much is going inside by various modes, either by transmission or by various modes of heat transfer. So this is defined as the solar heat gain coefficient. So it means that higher value of solar heat gain coefficient indicates more heat transfer from outside to inside. Okay, so if we want to reduce the building cooling load, we should prefer a glass or window which has lower SHGC value, or for a given window, we should somehow try to reduce the SHGC value in order to reduce the total heat transfer through the glass, right? Either through transmission or the secondary heat gain. So lower SHGC value is preferred, right? So in order to reduce this solar heat gain through window, we sometimes rely on the external shading, as Lal sir was talking about in the previous presentation. So you can actually, if you have a building which is facing north south, so and since depending upon the solar geometry, right? So if it is going through the top, so you can have this kind of shading which will actually cut down a significant part of solar radiation which was supposed to fall on the window, right? So that way you will be able to reduce a significant part of the heat gain through window, right? Because you are kind of cutting off the solar radiation, direct solar radiation falling on the window. Right, you can have side fins, you can have overhangs in order to reduce this direct solar radiation falling on the window, and that way you can reduce the building cooling load. Right, this is an example which is shown, and it shows that the SHGC value, right, in case of New Delhi, right? So this is for the unshaded case, right? So you can see the SHGC value is significantly higher. The red color basically indicates higher SHGC value. So it means if you have the unshaded case, in this particular case, there will be more heat transfer or more building cooling load which is contributed by the window. And the moment you shade it properly, so you can see that the SHGC, effective SHGC value is becomes lower, right? Significantly lower. Let's say from 0.65 to 0.4, right? So that way, I mean, in one sense, you have reduced it by a fraction of 0.2 or 0.25 amount of heat which was supposed to go inside, right? So by proper shading, you can actually reduce the heat transfer through fenestration significantly, right? So then you have this. Nowadays we use this double glazed window also, right? So this reduces, I mean, in case of double glazing window, you have two pane of glass, right, which are separated by a distance, right? And in this, you can either have air or you can fill some gas also, right? So in this particular case, there will be a radiation heat transfer between these two, and it is usually 2/3 of the total heat transfer. And then you will have a conduction heat transfer through gas or the air, and also the convection heat transfer, because there is some medium which is present between these two glass pane, and it can be either air or it can be organ or it can be any other gas, right? So you will have conduction and convection also, and it basically contributes 1/3 of the total heat transfer. Now, this effective means this way it reduces the overall thermal transmittance of the glass. Why? Because in between you have air between the two glass pane, and you know that air offers a significantly higher thermal resistance because it has lower thermal conductivity. So that way, this double glazed window, the U value or the thermal transmittance value of the double glazed window is supposed to be lower, right? And this radiation part, which is usually 2/3 of the total heat transfer, can be further reduced by providing a low emissivity coating towards the inner side of the outer window, outer glass pane, right? So because it has lower emissivity, so it will radiate or emit lower amount of radiation. So that way you can further reduce the heat transmission, right? So this is one of the way by which in a double glazed window, you can reduce the heat transmission by radiation, or you can reduce the conduction heat transfer by filling this particular gap by some gases which has lower thermal conductivity like argon compared to air, right? And then you have the convection also in between, right? So that can further be reduced by properly fixing the gap between the two panes, right? Or you can completely make it a kind of vacuum in between. So obviously, since there is no medium, so you will completely eliminate the convection heat transfer and the conduction heat transfer, right? So here the U value is shown for single glazing and double glazing cases. So you can see here that the moment you switch from single glazing to the double glazing, so the U value is reduced significantly. Okay, so the thermal transmittance can be reduced significantly by adopting the double glazing. Okay, whereas there is not much impact of on the SHGC value. Means although it is, I can say 10%, but the amount of reduction which takes place in the thermal transmittance is significantly higher, and obviously the cost of double glazing window is going to be higher. So in case of window, this VLT also is an important parameter. It basically talks about the daylighting efficiency, right? And the last thing is, so we talked about the SHGC value, right, of window or the fenestration. We talked about the thermal transmittance of the window, right? We talked about the U values, single glazing, double glazing. And the third important thing is the thermal transmittance of frame, right? We saw earlier that there will be some heat transfer through frame also. Now, depending upon the thermal transmittance of the frame, you will have either higher value, higher conduction heat transfer, or lower, right? So if you want to reduce heat transfer through frame, you can select the frame material accordingly, right? Say among the commonly used frame material, aluminium will have lower U value, obviously because of its higher conductivity, right? So you can select the material accordingly, depending upon their thermal transmittance in order to reduce the cooling load. So thank you. If there is any question, please feel free to ask so we can discuss it now.
I think everyone wants a lunch break.
Okay, so if there is no documents, we can discuss it later also.
Yeah.
So it's not a problem. So I think we should stop here now, and then when we can start next session. Sanji?
We propose to start at 2, but we overshoot by more than an hour. So maybe we should start at 2:30, or what do you suggest?
Here, 2:30, is it fine?
Sir, there is one question from Mr. Sheikh Sharma. So it goes like this. Could you please let me know about analysis of water vapor transmission through building structures?
Analysis of water vapor transmission through building structure.
Yes.
Means, is it through leakages or what? Like in the form of infiltration or what?
Mr. Sheikh Sharma, if you could elaborate, you can unmute yourself and elaborate your question. He write further. So like heat transfer through buildings, the moisture transfer through buildings, just like the heat transfer through buildings. So analysis, similar analysis for the moisture transfer also through building. So I think he wants to know about the moisture transfer analysis through building. If at all it is there.
So is it through envelope or what? Like
I think yes, envelope, yes.
Okay.
I can maybe.
Yeah, please go ahead.
I just would answer on this is that the heat transfer does not integrate the humidity transfer. What it can do with the heat transfer is to get an idea of the dew point of the surface or things like this to know whether there will be condensation. And at the same time, when you're calculating the heat transfer of air, that means the air entering with some humidity, then you will know more about the humidity change within the building. But the moisture itself, in terms of modeling, is normally done through the air transfer across the wall or by infiltration. So there is no generally specific, I mean, there are some ways of calculating the heat, the humidity storage in the wall. There are some specific materials, for instance, for libraries or where you want to conserve a humidity with less HVAC system. There are ways to improve somehow the humidity storage so that you avoid condensation. But basically, this goes beyond what is in the heat transfer basics that are covered by the book that Dr. Udaraj has developed. Am I right?
Yeah, so there is no mention of moisture transfer.
Yeah.
Oh, hi, both these speakers. This is Ghanshampal again from Shivnadar University. You know, the same question can be posed in a different way from the converse side, that presence of the moisture changes the thermal conductivity and the U values for the building envelope. And therefore the moisture, the mass transfer problem cannot be seen uncoupled from the heat transfer.
Oh, yeah.
I think that's right. What the speaker was trying to ask. If I can get some clarification, perhaps maybe I'm wrong, but that's what I think.
No, you are right.
Thank you so much. Thank you.
You are perfectly right on the principle, but only generally when we are designing buildings. We consider generally, for instance, whether it's concrete or what stuff like this, that when you are pouring concrete, you will need few months of stabilization about the kind of humidity that goes out of the concrete. But after that, the main issue is, you are right, that if you have moist material, the lambda value, the conductivity value may also change. But it's general of second order against, let's say, the heat transfer by infiltration or humidity transfer by infiltration or by HVAC system or natural ventilation. So I think that, let's say, the humidity transfer is much more important for physical damage, let's say. The building physics, if you do something wrong in the design, and especially I would say in Europe, in cold climates, for instance, typically if you are having insulation inside in buildings, you are often crossing the dew point in the structure. And that means wood may become rotten, or you may have damage because of condensation, or even swelling due to frost. But I would say in hot climates, this humidity issue is more like the dew point issue, that when you have, if you have cold ceilings, for instance, or slab cooling, you may have the dew point that goes above the temperature of the surface. So it's mostly, I think, these questions which are of very high importance when you are trying to go for radiant cooling, for instance, so to be sure. I agree with you, the humidity transfer, but I think it goes beyond what we are trying to do in this topic, but it's an important topic too. You're perfectly right.
Thank you so much, sir, for your answer. Thank you. Thank you.
Thank you all.
Okay, so we shall meet at 2:30 then, Sanji.
Yes, so we should start at 2:30. The lunch break is little shorter, but that way we will be able to finish in time.
Okay. So so we'll stop here for this particular session now. We'll meet at 2:30 again.
Yeah,
On next
2:30,
session.
the link remains same.
Yeah. So the link
Great.
remains same.
Okay, sounds good, sir. Thank you so much.
Yeah, thank you.
Thank you.
So good afternoon, everybody. I think we will start after 2-3 minutes because still people are joining. Okay, so good afternoon, everybody. So I think we should start our next session now. We're already getting late. So the next session will be taken by Mr. Pierre and Mr. Prasad. Let me introduce Mr. Pierre first. So he is associate at FNART Saal, Switzerland. So he has completed his master's in mechanical engineering from EPFL, Switzerland. He is associated with BEEF since its inception. He has over 35 years of experience and has been involved in BEEF's conceptualization and overall planning and management. He is actively involved in simulation and performance monitoring, CFD tool development, innovative technological solution, and supporting the IEA training activities on buildings. So, and our second speaker of the session is Mr. Prashant Kamre. So I have already introduced Mr. Prashant. So without wasting much of our time, let's start this particular session. So I will hand over this to Mr. Pierre now.
Okay, so I can. Yeah, so I will just share my screen. So you can see the screen. Yeah.
Yeah, it's visible.
Okay, so the idea of this presentation is to make a link, let's say, between the theory of the, let's say, detailed heat transfer, which are the fundamentals for engineering curricula, and how to try to make a link with how you could look at simulation as the next step after this kind of base training that you can have in the curricula, maybe at master level or in professional. So we did not discuss how long do I have to speak, Daraj, or how long can I?
Yeah, around 45 minutes.
Okay, fine. Okay, so I will first start by trying to look at explain a little bit the logic of the simple modeling concept of a zone, and then after I will speak a little bit about building simulation developments as well as the capabilities and few case studies, and then I will hand it over to Prashant for more case studies in India. So now if you just to call back, I think Dr. Daraj has already shown some of this thing, but just as a recap. So when you want to calculate the thermal power you need to cool a building, basically the first thing is to have the environmental data from a weather data, then to have the occupancy and heat gains inside. That means if you have computers, lighting, etc. And then you are looking at the building envelope, like the heat transfers by convection, conduction through the wall, whether they are opaque or whether they are windows where you add also some radiation. We will not do it for the simplicity today. And then you have natural ventilation or control ventilation, which is coming also as a whole. So if you look at the ambient, then you have the person, the equipment, then you have the heat transfer across the element, then you have the heat transfer across the glazing, then you have the ventilation, whether it is natural or not. Now, one thing I think which is very important to remember when we talk of designing buildings and cold and hot climates, and I think there is a little bit too much influence from cold country in the design in India sometime, in a sense that if you look at what is happening in typical winter, because we are still in countries in the north, you can say, where typically in winter you try to keep about 20-22 degrees inside the building, and with typically very less variation. Maybe you have some heat gains or or during the day, or some solar gain that makes a little bit changing but otherwise. And essentially outside the temperature is varying, let's say between 5-6 degrees and -5. So you have a constant flow from inside the building to outside, which means the more insulation you add, the better you are. When you look in a hot climate like India, most of the place in India, you have a very different thing, is that if you try to keep in the orange band your temperature, let's say in 25, 6, 7 degree, then what is happening is during day and night, you have a very big variation that makes that during the day you're getting heat from outside, and at night, if everything goes well, you are losing and trying to do even, for instance, night ventilation to cool, or so, which means the dynamic behavior in Indian situation is much more important. And I think this is important to remember, that you cannot just translate building codes from northern country or cold country into India, because, for instance, if you add too much insulation and you trap the heat, you will start overheating in an Indian context. So then here, this is just a little bit to explain the basics of, let's say, doing a zone calculation. So when we are looking here at a typical zone, or suppose you have here a fan coil cooler or a heater, and then you have, like in a calorimetric chamber, you would have controlled walls. So I show it here, it's by, let's say you have water pipes which are keeping the constant temperature inside the wall. And then you do simple calculation between what is happening between the heater or the cooler with the walls. Then the second level of modeling is, say, okay, you don't control anymore the walls, you let the wall being part of the game, and you have the temperature where you are fixing the node temperature, and then you are doing some few calculation. So here, what I try to explain is that typically it's not so difficult to start getting a simple model, which is basically, apart from the dynamic part, like you have in a simulation program for one zone. So if you start looking at the base, is that if you have, let's say, a fan coil or an internal AC component, if you have then what you have is that you have the cooling or heating system of the zone by convection in this case, which is taking care of the temperature of the air node, and it's giving heat to the air node or taking heat from the air node, depending if it's heating or cooling. Then after, what you have to look at is to look at the basic equation between the temperature of the air node and the walls. Here I have not shown windows to keep it simple, so it's only to explain that the heat between the air node and the surface temperature inside is this simple equation that you have the convection coefficient times the envelope surface that you have. Let's say if you take all the walls and floor and roof at the same time, multiplied by the difference in temperature between the air node and the surface internal. Then after, you have the heat transfer across the wall. Across the wall is that you are calculating the equation when you are taking only the conductivity of the wall as that means the resistance or and then you use again the surface, and then you have the difference between the internal surface and the external surface, which give you then the power, the energy transfer across the wall. Then after, you have the external heat exchange. Again, here I don't show the radiative part, I just show the convective system, but suppose the temperature outside is representative of a radiant, mean radiant and air temperature. So you say it's a combined, let's say, convection coefficient. So the energy losses are are the heat transfer coefficient times the surface of the envelope outside times the surface of the temperature of the envelope minus the temperature. And so then what you have just to do, is that all this in a steady state, that the flux will be the same from here to here, and then from here to here, then from here to here, and then from here. So you simply have to solve this few linear equation to get the balance of your zone. Now, if we take now examples out of this model, you can see that if you say I am a heating mode, let's say you have a temperature of 20 degrees inside, and we are let's say we are tuning the power so that the temperature of the internal surface temperature are at 20 degrees. It's not controlled, but it's let's say through the control, you could say you have a sensor that is keeping the temperature of the internal wall at 20 degrees by increasing or reducing the power of the heating cooling system. Then that means we would have this 20 degrees. Then we say inside, if there is no wind, we can say the internal convection coefficient would be in the range of 3 watt per square meter and degree Kelvin or degree C. And then, okay, and then you can see here that you have the same power going through if you recalculate all the equations. So we have a heat of about 640 watt to keep the air node at 23 degrees, which allows to keep the internal surface temperature at 20 degrees. And then the external surface temperature is very low at 0.4 degrees, because we consider a very high heat exchange, saying that there is something like wind at the same time. So this gives you an idea of a simple calculation of one zone. Now, if we say we are changing the U value of the envelope. So here you see that we have done it by keeping, we have a U value of the envelope in the range of 0.4. That means the loss coefficient of the wall is. Now if we come to this case where we say we have more like typically 200 mm concrete, or even or let's say bricks which are highly conductive, we would have a U value of the wall which is in the range of 2.4 watt per square meter and Kelvin, which is quite typical as a value of wall that you have. Then you see that by changing simply from 0.4 to 2.4, we get, for the same temperature inside, 23, and 0 outside, for the same component apart from the insulation of the envelope, you see that we go from 640 watt to 4,000 watt. So you see here the clear value of when you are in a cold climate, that the insulation is really the key. Now, if if we consider that you have no wind, and that you still have a wall which would have a similar characteristic of the conductivity, then if you reduce the wind, we had a wind of corresponding to making a heat transfer coefficient of 20 watt per square meter and Kelvin. Well, now we reduce it to 8, saying this is just normal combined heat transfer coefficient. We reduce then the power by a little bit more than 15% by just changing the wind. So you can see that with this kind of simple model, I come back to this, I come back to this model just to recap. You have the equation between the cooling or heating device and the air node. Then you have the connection between the air node and the heat transfer between the air node and the internal surface. Then you have the heat transfer across the walling, the envelope, let's say, and then you have the heat transfer coefficient and the transfer to the outside. So you see that so you see that with simple equation you can already look at some parametric variation and to understand better the coupling between the different parameters. So which mean by knowing what you can learn in the book of Dr. Udaraj, and by going a little bit further by coupling the equation, you can start doing what looks almost like a simulation model. It's really, you can say, primitive, but it's to explain that you can start playing with the different option. Then now we take the other case where we are going into cooling mode, which is more an issue, I would say, in India than so if we say we have 26 degrees that we are trying to keep inside the room, and we have a free internal surface temperature, that means we don't control this, we say it's just normal. Then we have a convective cooler, which is typically the indoor unit of an AC, typically. Then we say we have no wind outside, because often in summer, one of the issues that if you are very warm, in very warm condition, sometimes there is not much wind during the hot season. Sometimes there is, but sometimes there is not much. So you have this, and then we say we have a typical value of the envelope of 2 watt, a U value of 2 watt per square, which could be typically a brick wall, for instance, or something like that. Then in this case, if it's 42 degrees outside, with 26 and 42 outside, with the U value of 2, you can see that we are having a cooling, sensible cooling of 2,300 watts. And then now, the important thing is that if we have a much better insulation, then of course, when we look only purely at cooling at the moment, we are reducing, if we go from a wall which is at with the U value of 8, which was 2 watt per square meter in Kelvin in the previous case. Now, if we say we have typically 200 mm AC block, and that the U value of the envelope component, if it's AAC blocks, is about 0.7. So we see that we reduce the cooling power by a factor 2.5 approximately, which is logical. Everything is linear in this model, but you can see the coupling between the different components by using this simple equation model. And then after, the important thing is that if you now change the set point, so now you have this. Now, if you go from, let's say, 26 to 22 degrees, which is, there is always this debate about the set point on cooling, then you see that you are increasing by about 20% almost the cooling just by changing the set point. So it can show you already what is the kind of influence of different parameters. So this is just to show that by having the fundamentals of the heat transfer in a building, you can start playing with a set of equations, simple, solving them, and you already get, by combining the whole cases, you can get already a quite good understanding of how is the heat transfer going, even on a steady state to start with. And then after, you should add, I will show you after how you can go to simple model of equation based on some of the ISO norms. So this was a quick introduction to the, if there are some questions right now, maybe we can take them. at this level, because I think it's good to go back to it directly, or we can do it later, that as you want. Is there any question about this part? Maybe you can still go on asking later. So now we look at how a little bit historically how the simulation models for building have evolved with computers. I mean, with the much more common use of computers. So if we come back in 1958, there were already a couple of computers in the world, but basically most of people were relying on electricity analogy with the heat flow. And so you could see that people were doing simulation by using capacitance, resistance, and putting some power into it and measuring heat flows and capacitance being like the mass of a building to do a dynamic modeling of a part of a building. And this is an interesting paper which dates exactly 1958. And so this thermal electrical analogy has been used quite widely at the beginning, because when computers were not so powerful, people were trying to make simple assumptions. So this is just if you look at the different kind of analogy, that the heat transfer rate in watt correspond actually to the current in ampere in an electric circuit. The temperature difference across components correspond to the voltage difference across some of the component. Then you have the thermal resistance, which corresponds more to the heat transfer resistance across some component, like the conductivity, and this corresponds to electric resistance in ohms. And then you have the storage element, which corresponds to capacity, so which is in joule per degree per kg, or in joule per Kelvin per degree, which is corresponding to the capacitance you have in your model. So you can see here that the typical model with the simplified model that came in the kind of ISO model I will show you just after, is that you have a simulation with electricity, a network, but then after you transfer it into a thermal model quite simply, and that is how people have been developing early on, you can say, the models before computer was powerful enough. So you can see here a typical analogy, so where you have typically a wall where you have the resistance, which corresponds to actually the conductivity and the thickness, the resistance of the wall actually. So you can see that you can have this kind of analogy with electricity. And then you can also see that you have in this the capacitance as well. So now this is another kind of representation of the models. So you can see that often you have the external temperature and you have the surface temperature inside, and then you have the capacitance representing the walls on one hand and maybe the thermal mass inside, and then you have the resistance between these nodes, 3 layers with 3 resistance, and then you have this kind of model. And this is a more sophisticated model with electricity, which has been, I would say it was very common to see this development in the late 70s and early 80s. Again, when computer, let's say, personal computer did not have the power to run software like eQuest, for instance. For the one who know, a lot of you would know what is eQuest. That means this DOA2 model, which is publicly available and widely used in India. it would take too much time. If you would have, let's say, a PC in the early 80s, it would take days to calculate one case, and today it takes few seconds. But at this time, then that's why people were going on developing this thermal circuit modeling with the resistance. So I don't go into detail here, but you can see the principle of this modeling, and I think it is still valid for teaching. I think because you can show normally the engineer mechanical do also have a kind of training in electricity, so they can also get a quick understanding, or by analogy understand a little bit what is happening. So this model has been now actually relatively recently used again in the simple calculations for simple buildings for dynamic response. And this is the ISO 13790, which is exactly this model I was showing before. You have the air nodes, you have the surface nodes, and then you have the mass node, and you have the difference, the ventilation, the transmission across windows and opaque, and then you have the external flux, and which give you a model. And it is actually, it's what is interesting is the reference I have given here. You can see that people have now done some study. So on the left here, you have Energy Plus, which you can say is today, I would say, the state-of-the-art, best validated building simulation model. And you can see that for heating and cooling, of course, it is reverse. This is for basically cold climate case, but for a hot climate, it would be the reverse. So, and here it's the yearly heating in blue. So you can see that with Energy Plus, for the same parameter given, using the two ISO norm, which are this ISO norm I showed you before, which is using, and this one, which is a slightly different electricity analogy. But you see that basically the heating demand is very, in the few % the same, and the cooling is also the same. So again, be careful here. This works only for very simple kind of box building simulation. It would not work at all if you take, for instance, a commercial buildings, or if it works for a sophisticated, let's say, hospital or something. You cannot apply this. But for, let's say, residential housing, if you want to get a quick analysis without using, of course, it will take, today it will take you as much time than if you were using actually a simulation tool, because now inputs in simulation tools are so fast that there is no use to make a difference and go back to this. But as a teaching tool, I think this analogy are quite interesting, because you can really get the student to do some basic equation and understanding of what is happening. So now, if we look at the simulation software, what is also important to know is that since the beginning of, let's say, the development of the simulation tool on a wider scale, like in the, you can say, the mid-80s, you can see that there has been, for IEA, which stands for International Energy Agency, they have developed very quickly what they call the best test, which is a kind of comparison on typical case between different programs, and some of the case they had an analytical reference. So you can see here, this is the kind of analytical reference. That means it is a calculation which can be perfectly calculated by a mathematical equation. it's not such a complex system that you would need a purely numerical solution. It's really something that can, and then you can see here, for instance, for different software, going from HTB, which is an old software in UK, then ESP, which is an energy simulation research program that has been used mostly in was development in Scotland. Then you have Transys, which is the well-known software. You have Transys and Comfy, which is a French software, and O2, which is actually the engine for eQuest. So you can see that basically after some years of comparison and bug checking, this was in 2008, so it's not so old. You can see that there is a good agreement between the different software for this kind of test, and that they are matching well with the analytical solution, which is in this case possible. But again, this is the analytical solution is one case, a few cases, but many cases, and then they have been contradictory simulation between different software and see how they vary. So here you have something which is more recent. It is the difference between different software. So you can see that depending on the generation of software, you can see, for instance, Do2, which is, you can say now, a software which is again the engine running eQuest system, which was one of the reference in the 80s, is now somewhat lagging behind. Then you have Transys in red, then you have Energy Plus. So you can see that Energy Plus Transys, they are matching better, but you can see that Do2 is somewhat not anymore up to the level of more complex things, like when you add overhangs, when you had fins, when you had different strategies. You can see that this software of older generation are less accurate because they do not take into account properly all the particularity. And for instance, typically we can see that Do2, the eQuest engine, is now typically overestimating the cooling loads as compared to what you get with the, let's say, the up-to-date software like Energy Plus, which is really, you can see that Transys is also quite near. They agree. The red ones are the ones which are more reliable nowadays. And this is another validation to show you an example of some of the empirical validation that have been done in the International Energy Agency task. So this is not of direct interest for India, I think, but it's just to show that double facade, the double skin facade, which is always a headache for designers, because thermally it's always very difficult to calculate and to validate between heat transfer, mass air, mass flow, and all this, and the radiant aspect. But you can see that the so-called modern software, they can quite well compare with measurement on one hand, and with also between themselves, between different software. You have this Transys, ESP, and then VA114, which is a Dutch program, and you can see that they are matching well with the simulation, with the measurement results as well. So now, when we talk of simulation softwares, as I showed you now, you have this simple simulation. So this is typically something that you can do as an exercise. In addition to the heat transfer later, you could develop things where you give them an example of doing some simple simulation using this analogical electrical, so that people can maybe better relate to the heat flux and the current, etc., and understand this by two different modeling. Then if you look at now the more comprehensive software, I would say, essentially, I think, and this is Energy Plus, which is, let's say, the state of the art. It has got good interfaces like Design Builder, but of course it's commercial, it's not free. Some people are using some other interface, some other are free, but they are I think the productivity design builder is certainly a good interface, but the problem is that it has some limitation because this interface are not able to deal with complex HVAC system. But this is not really an issue for you in terms of teaching. Then Transys, of course, is a more modular, flexible environment. It's quite easy to develop your own component even. And it's also very easy to, not easy to use, but it's much more easy to understand the building, the code, because the code is very modular and you have access to the source code. So it's also an easier relation between the equation explaining things and actually the trend. And then there are other comprehensive commercial software, but I would say the issue with this software like IES or TAS or some other, they are in principle quite black box in the sense that you don't have access to the source code, and therefore it's more difficult to teach also and to use it if you are a little bit curious about the results. So I will just show you how simulation has been applied for different projects. So this is a quite big building of the United Bank of Switzerland, which has been now taken over by the Zurich city as an administrative building. But we had done very long time ago a retrofit analysis of this building, which was mostly considering the HVAC system. It was done with Transys with a special model for HVAC air handling units. And you can see here a view of the 3D of the building. And you can see here the different systems. And of course, at this time, there was not so many detailed model for HVAC. So in this case, we had to develop a model for specifically to be able to simulate the complete system. And therefore, we had developed this in Transys because, as I told you, it is a more flexible environment to do. And this helped us to do a detailed audit of the building. And the interesting thing is, in 1988, they had already done quite few saving measures, energy saving measures. And so we could have the measurement from 1976, which was, let's say, the original state of this building. And then we could get from them the actual energy bills in 1988, which was after improving the HVAC by adding some heat recovery, which was not there before, by changing some of the set points, by optimizing flow rates, etc. And then you can see that we could get, and this was more like a blind test. It was not that we played with the number to make it similar, but you can see that typically, globally, we could reproduce quite accurately what was happening in the real condition of the buildings. This was done as a research component of one of the International Energy Agency Annex 21 of the energy conservation in buildings, which was appropriate use of simulation models. So it was really about the methodology to make a proper simulation. Then another thing which is also interesting is to see that we had in a building which has been built in the late 90s in Switzerland, which is the Swiss Federal Office for Statistics, and which is one quite low energy building, but which is essentially naturally ventilated with external movable shading. And before it was in operation, we could isolate some zones and actually test with internal gains. With simulation of internal gains, we could compare the simulation and the actual results. And you can see here that between the measurement and the simulation, it's matching quite well. When we have the dark black is the temperature outside over 3 days. And you can see that the temperature in the zone confirmed that we could stay below the external temperature by about 3-4 degrees. as compared to a building which without shading and without proper natural ventilation strategy would go well beyond 30 degrees. So I think this is quite an important experiment that we could have and confirm that the design. So now if we compare the results and the prediction, we got a special system in this building with a data center which was delivering some heat that was recovered for the heating of the building. And you can see here that the actual the prediction when no data center, and then with data center which was in between, we had two different scenario. At the end, see that we are matching quite well with what was predicted, or the scenario was 40 kilowatt, which was near, and the electricity was even lower, but that's because of optimized operation. But you can see that prediction and actual monitored data were matching quite well. Then another case study about design with different simulation tools is the Rolex Learning Center in EPFL, which is now surrounded by more buildings, but at the time where it was built, it was like this. And it was designed by the Japanese architect Sana, and it was a quite peculiar building, which is of course the EPFL did not want to have the whole building under AC. So we had to design it for natural ventilation. For a building of this shape, it was quite a big challenge. And so you can see here that this building was completely protected with external shading, which would have been which was the only solution to avoid really overheating in such a building. Because if you think of the glazing area that you have, it's huge. By the way, BIP will soon publish the results of the testing of external movable shading in a real situation in Gurugram, where we could show with BIP that the results are giving excellent result when you are using external shading, which is not so common in India. It was common in old buildings, but it's no more. It has to come back because you can reduce cooling loads up to 30% in buildings, typically as a kind of ballpark number, by having external dynamic shading. And so here, what was the challenge was to have two things. Is that on one hand, we had to simulate the building hour by hour to check the overheating risk. And to do that, we had to develop two simulation model. One was with transits, where we had a complete kind of network. You can see all the zones with the different relation between the zone for air change and the zone that were under simulation in this building. And on the other hand, we have to do a computational fluid dynamic simulation to really look at how the air was moving when we are opening the different possible openings, and see how with the stratification, because it's a building which is flat but which still have this kind of variation in height. And so what was done here is to also compare on a steady state the temperature calculated with the computational fluid dynamic for a steady state, and at the same time we were also comparing with the dynamic simulation model if we would get similar temperature with a constant weather condition comparable to this one. So when this was done, we could do the complete study of the natural ventilation openings, and there were dozens of iterations with the architect until we could get a satisfactory answer. So we had this this difference between the simulation with the CFD and between the Transys model or the dynamic simulation model. You can see that they were matching quite closely. So we could really then so this building has this peculiar feature that it has this automated control of the external lamella blinds. Also the openings. There are 127 motorized opening. You can see here the chain, if you look well, the chain motor, which are opening the natural ventilation opening by in different at different level. There are 2-3 different level of openings depending on the wind condition and depending on the temperature. And then you can also see that, oh sorry, we also have openings at the top where the higher location are. There is the restaurant and the library, which do have this direct opening so that natural ventilation can get an exit also nicely. So this building has been behaving like it was really planned. That means we never got more than 28 degree in the building when it was 33 outside, even though it's a quite peculiar shape for a building, if we, of course. And here, this is to show you also that when we do new building or retrofit, we can also predict quite well what is going to happen. So you have here a project where you can see the new construction part coming. And then here you can see the new part as compared to the ancient part, which is renovated. And in this case, we had the quite detailed energy balance of heating of the commercial part. These are the EPI in energy, in final energy, and energy consumption. You can see in orange, you have the predicted values, and in dark red, you have the actual monitored values. So you see that if you are using correctly, if you have proper scenarios, and if you have proper, which is very important, proper scenarios of occupancy, of internal gains, which is of course not always easy. And if you do a proper, let's say, introduction of the data of the building with including, let's say, thermal bridges and different things that you take care of, you see that you can have quite good results with simulation, which are all based actually on, you can say, the basic of the building physics that you get in the heat transfer curricula. So I think now I would just like to conclude by linking to the Indian context, and I think what is very important is that Professor Lal this morning showed in his presentation also that reducing heat gains through the building envelope is something which is very important, and we see still too many projects where people are going for this kind of highly glazed system. And if you compare this with such a building like the Development Alternative Head Office, for instance, in Delhi, you can see that we have seen project where if you calculate the heat loads, they can go up to 150 watt per square meter of floor area in this kind of building. And if you do a proper design with less windows, with better thermal mass, and if you have also proper shading, then you can go down from almost 150 watt per square meter down to 8 to 15 watt per square meter internal, let's say, external loads into the building. So you can see that the cooling system will not be the same size, definitely. And it's not also the same thermal comfort, because if we were talking about internal surface temperature, if you are near the window of such a building, you are getting the glazing which have some kind of absorption of the heat, which will just heat you if you are sitting nearby. So you will have very high internal surface temperature. So a lot of discomfort apart from glare and other things. And here I would just like to make a small, not remark, but a compliment, maybe ASHRAE 55, which has been used in the presentation of Dr. Udaraj. I think it would be good also to add what has been developed recently in India, the India model for adaptive comfort, which gives a range which is a little bit higher than the ASHRAE 55 for comfort, but which is based on quite a lot of study and questionnaire to many people, and I think this is, to me, more relevant now than ASHRAE 55, I would say. So, to give just a few conclusive remarks, I think the fundamentals of heat transfer are really necessary for the engineers. I think here, especially on mechanical engineer, but structural engineer as well. And if you want to use simulation software later in your career, if you don't have the fundamentals, then you cannot use them wisely because you will not understand the thing. So that's why the fundamentals of heat transfer are really very important. Then another thing, which is both for architect and engineer, there should be a good teaching about building physics in relation to the real process in buildings. And it should be taught also as well, also for architects, not only engineers. So this is something, in my opinion, which should be further developed. Then the engineering assistant to architects is, of course, now very important because we can see that if we take this example, if you leave architect do this, it's really a sad thing, because at the end it costs more. It will use 3-4 times more energy. So if you think of climate change and energy efficiency globally, it seems that it's really this kind of building should disappear somehow, or at least no new building of this kind should be constructed. Then so the heat transfer applied to building, I think it's an important thing, because there are two things. I think the student, I would say mechanical engineer generally, and it's not only in India, we have the same kind of consideration, I would say, in Switzerland. People coming out of mechanical engineering, they often do not have a specific topic on building science, or if they have, it's a minimal, and often people don't see the interest of building science, or let's say working in building. They have the impression that this is something which doesn't move. Actually, building is something which is fascinating in terms of modeling, in terms of analyzing. So I think I think it's very important to try to get mechanical engineer more interested in buildings, because very often they just are not aware that there is something to do with buildings. They think it's just architect and draftsman who are just making the building and that's it. It's not the case. And so I think this basic training in heat transfer is fundamental for mechanical engineer when they will go for use of software, if they join companies in the range of in the domain of building consultancy and energy. So this is the end of my presentation. So please, any question or remark?
I think there are 2 questions in the chat. Here you would like to read and address them.
Okay, I have
to. I read it for you?
But wait a minute, I have to go back here. And where is the chat? Okay, the chat is how to account operative temperature in this heat transfer equation.
I think it's about the initial steady state model.
Oh, about the initial steady state model. So in this steady state model, again, I thought what I have shown is not a very complex model. It was just to explain a little bit the principle. So now, if we go back to this simple model, if you, sorry, what is the? So here, what you have is we have considered only the heat transfer coefficient where we have a purely convective heating or cooling system. So if you have a radiant cooling system, of course, it would be different. You should add the part which is the radiant, and then the operative temperature become then the combination, the calculation, typically half-half. You take half of the mean temperature, mean radiant temperature, that means the temperature you have on the surface, and of the air temperature. And normally that's how operative temperature is calculated in all the simulation. So it's quite easy to add. I have not shown it here. It's a good suggestion. We could also make a model where we show the idea was to show how you can make the balance of a zone simply, but clearly we can add also the equation with the heat transfer. Does it answer, or? How to validate the simulation output with real life situation? What do you mean exactly by that? Because I have shown you that we and Prashant will show also in his presentation now case study where we can see that we have this kind of validation in a sense. Validation is a strong word maybe, but good comparison between the prediction and the actual results in the Indian context. So I think the answer you will get through Prashant presentation, who will present a few case studies in the Indian context with actual comparison between prediction and actual results. I think we can come back to it at the end of his presentation. So I think then we should shift to. We are ready for question at the end of Prashant presentation because it will complement, I think, what I have done now. But if you have any urgent question, please.
I can wait. No issues. I can wait. I can wait for Prashant.
Okay, so I think I think the best is to go through Prashant presentation and then you can. Yeah. Then you will get mostly your answer, I guess.
Okay, so let me share my screen. Okay.
Hello.
Okay, so is my screen visible?
Yeah, it's visible.
Okay, do the full screen. Okay. So I'll be going to present two case study, which is of course in India. One is a commercial building, fully air-conditioned office building, and the second one is affordable housing building with no air conditioning. So there we will see the thermal comfort or inside temperatures, and the first one where we are looking at the case study of commercial building, we will be looking at the energy performance. So before going to the case study, just reiterating the approach. So you start with the business, the first level of design. Then the first step, what you need to take is to look at the passive measures. The aim of this passive measure is to minimize your requirement for thermal comfort as well as lighting purpose. So then there are ways, I'm not going into those detail, orientation, window sizing, insulation, all those measures can be sort of explored, but the end objective is to reduce or minimize your requirement for thermal comfort and lighting. Then comes the selection of thermal comfort system. And then here the objective is whatever your requirement is, you try to meet it to the most appropriate and efficient system. So the air conditioning system lighting system, we saw radiant cooling system can help a lot. So all those things needs to be sort of selected and designed. Then comes the last step, that you will be requiring some energy. So if a part of it or the whole part of it can be supplied through renewable energy generation. So that is the overall approach for energy efficient building design: reducing the requirement, selecting system or designing system to meet those requirements, and supply a part or the whole part of those requirements through renewable energy systems. And the second thing is then when you try to follow this approach, so it is highly recommended that it is done at the early design phase, trying to incorporate all those design changes, and then involving the entire project team, starting from the client, architect, air conditioning engineers, structural and green building energy consultant. So what it shows that if you are at the beginning of the project stage, then you have the maximum potential for saving the energy. If you have designed something, already frozen few things, then the potential for saving energy will reduce. Similarly, on the cost part or the effort part, if you are at early design stage, then your effort or cost would be minimum. If you are trying to integrate things later on, once few things are already frozen, then your efforts and cost will go up. So it is recommended that the this design charrette or design workshop is done at the early stage of the project. Okay, so this is this slide shows different type of projects which we have done under the BEEP, and it shows the EPI or the energy performance index in kilowatt hour per square meter per year. So you can see there are a variety of buildings: public office building, private office or IT building, training institute, educational institute, and hospital. And the blue bar shows the EPI, what was expected before doing the design workshop. And these are the revised number after we did the design workshop. We sat with the entire project team, came up with the possible energy saving interventions, and then we predicted the energy performance through simulation. So all these numbers are based on the simulation, but I will go to the next step, where we also did the performance measurement and also tried to validate the simulation findings or the simulation results. So I'm taking the example of Aranya Bhavan, Jaipur, first building which is air conditioned, and the second one which is not listed here because that's an affordable housing project, and we did not calculate the EPI and all. We sort of predicted how would be the internal inside temperatures in the building or the thermal comfort. So let me start with the first case study. It's an office building in Jaipur. It is the head office of the forest department. It was inaugurated in March 2015. It has a built up area of around 10,000 square meter, excluding the basement and service area. It is ground plus 4 building with one basement, and it has about 350 users. So it's I would say it is in terms of occupancy, it is not like a private office building where occupant density is much higher as compared to this building. So occupant density is slightly lower in this office. And then in addition to the office space, you have a museum, library, auditorium, and even they have 4 or 5 rooms, guest rooms in the building. If you see the location, it's Jaipur and it falls under composite climate. The graph here shows the annual temperature range. It shows the minimum and maximum range and a kind of average temperature for each month. So let me go to the next slide, where these are shown in more detail. This is a monthly charts, monthly average chart. The blue one is the solar radiation. It's in watt-hour per square meter. And the orange one is the dry bulb temperature in degrees Celsius. So what you see that overall, there is a high amount of temperature. You can particularly see in the month of April, May, June. May is quite hot. Average temperatures reaching 40, and also a high amount of solar radiation going up to 1000 watt-hour per square meter, and so. And the winters are there. It's not too cold, I would say, but there are moderate cold season as well in the month of, say, January, December, this month. So when we look at the weather data, that the objective becomes very much clear, that we want to reduce the heat gain from the building envelope and it's a daytime occupied building. So we wanted to reduce the heat gains from the building envelope in terms of passive measures. And of course, we would like to design the air conditioning system with the system which gives you best efficiency to meet air conditioning requirements. So when we started or we first interacted with the design team, the idea was to have a kind of building envelope with the wall, normal brick wall, which will have a U value of about 2, roof, normal concrete slab roof with a U value of 3.2, and single clear glazing with the U value of 5.10 and very high SHGC of 0.8. And then during the charrette, we were able to sort of demonstrate the saving and convince, and these are the things which is actually implemented. So the roof was insulated with the 40 mm puff insulation, and the U value from 3.2, it was reduced to 0.6. And the wall also was insulated, so it has a cavity wall filled with insulation. So 50 mm XPS insulation was added in the cavity, and U value we could achieve of 0.5 watt per meter square Kelvin. In terms of glazing, first of all, we made intervention to reduce the glazing area itself. And then we selected efficient double glazed window system, which gives a lower U value, lower SHGC value, still a decent light transmission value. So this was the passive measures which were integrated in the building. So just to sort of link it with the heat transfer book, which Dr. Udairaj has prepared. So this is the example calculation from for this building, which is also added in the book. So what it shows that how do we calculate the impact of passive measures if we add insulation. So the solid bars are showing the heat gains or heat flux for the normal case, and the filled one, the adjacent ones are showing numbers for with insulation. So you can see if we add insulation for wall as well as roof, we were able to reduce almost 80% of heat flux through the wall and the roof. And then like once we have selected this kind of passive measures, then there is a significant reduction in heat gains coming from the building envelope. And that will certainly help in reducing the cooling system size required for the building. So like what I told, that before the adding all those passive measures, the cooling system size was around 230 tons. And then after we added all these measures, then the cooling system size was reduced to 165 TR. So there is significant saving in cooling system size reduction. So so while we say that, okay, energy efficient building and making all those measures does require additional investment, so those investments are also get compensated through these type of savings. So for example, here you will require reduced capacity of air conditioning system. The capital cost will be low. Your contract demand will go down. Your power backup for DG sets will go down, and all the cabling and all those electrical system specifications will go down, and there will be a cost saving in that. So coming to the air conditioning system, when we got into the Chariot, the initial design was to go for the air-cooled VRV system, which will have a COP of around 3.5 or so. So what was proposed and implemented is water-cooled centrifugal chiller, which will have a COP of 5.8. And there was a question that there will be, sorry, how they will get the water. So then the solution was that they will be utilizing the water from the wastewater treatment plant. So a wastewater treatment plant gives supplies water for the cooling tower, which is required for the HVAC system, and then it is sufficient to meet the water requirement, and we are able to get a high chiller COP system. So that was all the design part and the all the measures which were integrated. Then we after the building was fully occupied and operational, we did detailed energy monitoring for the performance, tried to see what we predicted and what do we get. These are the some of the photographs. We sort of did a lot of electrical measurement and the detailed analysis and measurement for air conditioning system, because that was the that we know that in air conditioning system HVAC will contribute the most. And also they have installed a solar photovoltaic system, so we also sort of monitored the performance of solar PV system. And that the monitoring was done sort of strategically to look at the two extreme seasons, the winter month, 2 weeks of monitoring in winter and 2 weeks of monitoring in summer. And we used 1 month of electricity bill to compare. So these are the results. So these, so again, these are for winter months, November to February, when the air conditioning system was totally switched off. So that's why you see HVAC as 0. And then the office equipment were the major energy guzzler. followed by the lighting. In summer, the picture completely changes. HVAC becomes the biggest component in energy consumption, and then office equipment remains the second. So this was to see how the distribution is there in winter and summer. Just to overall picture as an annual basis, HVAC still remains the highest, 53%, more than half. And then office equipment 31, and lighting remains small, only 6%. And we further looked at the breakup of air conditioning. So in air conditioning, the chillers take maximum part of it, more than so out of this 53%, more than half is taken by chiller, then AHU and all the pumping and cooling towers, etc. So this is what we could get from the energy monitoring study. And now, after getting all those data, we sort of compared what we predicted during the design workshop through energy simulation, and what we actually measured. So, and again, this shows for the data is shown for every month, and then we are showing EPIs for every month. So the blue one is the simulated, say for example, 5.5 kilowatt hour per square meter per month for the month of May. That is what was simulated. And this is what we got through the actual monitoring. So it shows a good amount of agreement between simulated and actual result. You see some variation in the winter part. So there in simulation, we considered that they will still be using like if it is required for heating, then it will be used. So and then what we observed that during these months, no heating or cooling was done in the winter months. So people adapt with clothing, and there was no heating done as such. So the actual EPI of this building is 43 kilowatt hour per square meter per year. And just to compare, the B 5-star benchmark is 90 kilowatt hour per square meter per year. So it is even half of the requirement for 5-star rating. So it is it probably will get 7-8 star or so. So that was on the all about the first case study on commercial building. The next one is an affordable housing building project, which is called Smart Ghar 3, which is there in Rajkot. So Smart Ghar 3 project it's a residential building, as I said. There are about 1176 two-room apartments, compact houses, only 33.6 square meter of area. And as I said, it's an affordable housing project. So most family will not be having air conditioning. And the idea here was to see how the building performs with passive measures and see the inside temperature and thermal comfort condition and how it can be improved. So we did during the design workshop, we did some studies with their sort of existing design, and see how much heat comes from which component, and then So just to show that the glazing was contributing maximum to the heat gain, and followed by the walls, and the heat gains due to internal loads were not much, because it is expected that occupancy was certainly significant, but that we cannot do anything about it. Rest of the things which can be managed, we tried to propose measure for that. So the first thing was the glazing, and just to tell you why roof is not coming here, is that we did this simulation for the intermediate floor. So and we considered it to be adiabatic from on the top and bottom. So roof study was also done for the top floor, but this result are showing only for the intermediate floor. So yes, we found that okay, there is something needs to be done for the window and the glazing part. So what was suggested and eventually implemented is, the first thing is we tried to reduce the window to wall ratio. The window sizes were slightly reduced so that the heat gain from the windows can be reduced. And then the window design, if you see, it is only part, only 1/3 of it has the glass, and the 2/3 roughly is opaque. So so the direct solar radiation from the bottom 2/3 part will not be coming inside the room. And then it had, the earlier design was that it will be having sliding windows, which you will not be able to open fully. With the casement window design, it is possible to open the window almost full. Coming to the wall construction, 230 mm AC block wall were proposed and sort of made, and we could achieve a U value of 0.8. And then on southern wall, we went for the AC cavity wall, which through which we got a U value of 0.3. So which is quite good in terms of reducing heat gains through conduction. For the roof, high reflective glazed tile was implemented to increase the reflectivity, so that the less amount of heat is absorbed and further transferred inside the rooms. And so like these are all envelope measures, and when we developed this residential building code, we tried to simplify the things and to understand how much heat gains are happening through the building envelope, and what could be the benchmark number to when we can say that okay, this is a good building envelope. So for that, a term called residential envelope transmittance value has been derived, which is essentially combines the heat gain through conduction from the opaque surfaces, or you can say walls, conduction through non-opaque surfaces, or you can say glazing or windows, and also the solar radiation through non-opaque surfaces. So direct heat coming inside to the rooms from the windows. So all these heat gains are combined in one term, which is called RETV. If you look at the things which will affect RETV, I will come to the definition of RETV in next slide. but the variable or the parameter which will affect RETV will be the walling and wall construction, because which will govern the heat transfer through the walls. Window to wall ratio, how much window area is there. U value of the glass, which will govern the heat conduction through the glass. SHGC, which will govern the direct solar radiation through the windows. Shading of openings, which will sort of help reducing the solar heat gains through direct transmission. And also the important thing is the direction of wall and openings, because in all, as per the orientation, the heat gains will be different for all the components. So now coming to the what is this term RETV, or residential envelope transmittance. So the definition is, it is the net heat gain rate over the cooling period through the building envelope, excluding roof, of the dwelling unit divided by the area of the building envelope. And this is the formula for to calculate the RETV. And what does the Eco-Niwas Samhita or code says, that the RETV value should be less than or equal to 15 watt per square meter. So that is the number which one should aim for residential for the building envelope, and the RETV should be less than this. So it as it says, it's a combination of those three gains. So the first term corresponds to the depends on the wall properties, and the second term depends on the window properties, and the third term also depends on window property as well as the shading part of it. I will not go into too many details of each of the term and all, but this is you can get more details in the code document. So the RETV for this project, the Smart Hut project, which was calculated as 9.5 watt per meter square. So it is much below than the required ENS norm of 15. So you can say this building will have significantly lower heat gains from the building envelope. So in addition to the building envelope measure, there was one, I would say, innovative system which was tried and tested in one of the building blocks, is that to have a assisted ventilation system. So in one block there are 7 stories, and 14 the common shaft is connected with the 14 flats. So on the top there is a common exhaust fan, and when the fan is on and the windows are open, the air can be sucked from windows, and then it goes through the entire room, and then it goes out through the shaft, and then gets out of to the atmosphere. So so the ventilation inside the house can be significantly improved, and the one fan can provide like this sort of common system can provide good amount of ventilation for to all the flats which are connected through this common shaft. So as shown for the commercial building project previously, similar kind of study we have done for this project, that is the energy monitoring. I would say thermal comfort modeling in this case. So we did the monitoring in summer months, because that is the season which is more critical, and we wanted to make sure that what we predicted for worst condition is more or less similar to that what we predicted. So this is what you see the graph. There are three lines. The red one is the outside temperature. The green one was the monitor temperature, and the blue is the simulated temperature. So what you see that there is kind of good agreement between what was simulated and what was actually monitored, and both are quite quite below as compared to outside temperature. So roughly you can see the temperatures are going up to 40, and you can get inside temperature 32, 33. So there is a good drop of 7-8 degrees as compared to outside. And just to tell you, with the initial design, the inside temperatures were going up to 38, 37, 38 in that range. And from there, we could bring it down to 32, 33 degrees Celsius with all these passive measures. So yeah, so that 32, 33, what it means, Pierre also spoke about India model for adaptive thermal comfort. So it is, right now it is developed for with the studies based on commercial building, but it is quite relevant for Indian context. And there is another set of IMAX study going on specifically for residential buildings. So the IMAX band for residential would come out, but for the time being, we are using IMAX for commercial building version for residential as well. So what it shows that for each month, so the idea of adaptive thermal comfort is that based on the outside air condition, we can feel comfortable. If the outside is higher, then we can feel comfortable even at slightly higher temperature. So that is the sort of concept of adaptive thermal comfort. And then what you can see that in the month of May, the adaptive thermal comfort band suggests that if you are between 28 and 32 or 32.8, even that, then you will be you feel comfortable. So that is what roughly we could also achieve, that even in the hottest months, we were able to manage temperature condition within the thermal comfort band. So quickly sort of summarizing that integrated design approach with good engineering analysis done at initial stage can help bringing down a significant reduction up to say 40% in terms of energy consumption, and also significant improvement in thermal comfort. And like nowadays, the simulation tools are quite powerful and quite reliable also. So one can take design decision based on these simulation software quite confidently, provided they are used well. So the efforts, what is required, that to improve the skills or knowledge as well as number of building sector professional, making available new tools for analysis. One such effort under BEEP is being done, that we have developed a CFD simulation tool through which, and it will be open source and it will be available for free. There you will be able to do CFD analysis for the buildings, and which can be very useful when designing the building massing, and even do some internal CFD to design the placement of windows, sizing of windows, and all those can be sort of well calculated and decided and designed. Yeah, so, and then the sort of approach and working process that there is a need to practice the integrated design practice, because if the team doesn't comes to a common conclusion early at the design stage, then it is highly unlikely that we will be able to get the best design solution for that building. So it is important to practice the integrated design model. So thank you from my side, and if there are any questions, then I'll be happy to answer them. Just one thing, I think, let me, before question comes, there was a question about the cost part. So this project, Aranya Bhavan, so for cost was 2%, and the payback period was slightly less than 3 years. Okay, so if there are any questions, then we can take it up.
So I think Professor Gunjan, your question is already answered. If not, please let us know. Yes, okay. Yeah, Dr. Ghanshyam was asking something earlier.
It's more of a curiosity, Dr. Udairaj.
Yeah, please go ahead.
And the question is that, you know, we have all these glazed building, the building when the fenestration is completely glazed, which the earlier presenter showed. You know, and I wanted to ask him, you know, in his opinion, what can be done to improve the energy efficiency in such kind of existing structures? Basically, the rehabilitation from the energy efficiency point of view for these highly glazed buildings. Can some, you know, this externally moving shading, which we were talking, can that be helpful? Or, you know, changing the glazing, applying some glazing film can it be helpful, which, you know, stops short range, short wave radiation completely, those kind of things, approaches. So that's what my curiosity is. And if I wanted to, you know, thank you.
Shall I can just give a quick answer or some clue, some idea on this. I think obviously if you take, for instance, the Swiss standards for facade, which is the most stringent in the world, I think. It's not because it's Switzerland, but it happened to be so. Huh? And we are, if you have a building which is 100% glazed, you must demonstrate that your solar heat gain coefficient is below 8%. That means you are entitled to have all the glazing you want, but you must protect them so well that either by external shading, mostly by external shading, that's the only way to reach this, because even if you have the so-called electrochromic glass, even if they are in the lowest, they are much higher than this, and also they have a much higher temperature as well. So the actual SHGC is much higher. But if you, but the issue is more that on large and high rise glazed buildings, if it has not been planned to have external shading, you know, to have external shading that can survive with wind and even with typhoons once in a while, you need to have a special thing that generally the glazing is a little bit in a recess, and the external shading is not out of the plan of the facade. If you want to, you have the facade like this, then you have the glass behind, and in between you have then the shading which comes, and which could be even with the glazing outside. But doing this retrofit means changing all the element of the facade. It's very difficult to do it otherwise, because otherwise if you add, let's say, kind of light fabric on a 25-story building, then when there is wind, it's likely to go away. So I think it's, to me, the solution is to have a mandatory requirement which makes, actually, if you look at ECBC now, at least you have no more normally than 40%. But you can still demonstrate that you can go above by doing tricks here and there. And we can see that a good play of the consultant is to try to get more glazing by playing with different parameters. And so I think that the external shading is very valid for building which either already have this recess. If you see what Professor Ashok Lal have shown of some as his example, his window are normally always a little bit inside the building. They are not just up front, so that lets the space, and to have something that is not getting the wind directly heating or taking it out. So for new buildings, we should have something that, even if suppose you don't place the shading, there should be a place for the future, so that you will be able to have, because this is a tremendous change. Of course, if you still have very high power inside after, because you don't have energy efficient IT equipment, for instance. But if you see today, take Infosys, for instance, what they have done, they don't have external shading, but they have reduced significantly the window to wall ratio. They have added some kind of overhangs, which are supposed to be light shelves. I'm not sure it's fully optimistic, but they're optimal. But they get something like 80% daylight autonomy in their office because they make relatively shallow plates, and they have radiant cooling with high temperature, high performance chiller. So they get numbers in the range of 60 kilowatt hour in their buildings now for quite dense occupation with the software developer or IT. So you have demonstration in India that it's possible to make buildings in the range of 40 to 60 kilowatt hour EPI now, and not 200 like a study by Enzen a couple of years ago showing that commercial buildings in Bangalore were in the range of 300 kilowatt hour. So it's really architecture is the first thing, definitely. Second thing, and then after, to plug in high performance HVAC system. And so if you have these two, try to use maximum high temperature radiant cooling so that you can run also with very low approach cooling towers, sometime directly. So you have a COP of 40 instead of 3-4. So there are a lot of things, but it's a system. You have to put all this together if you want to make a high performance. We are working with Professor Lal on a net zero energy building. I cannot speak too much about it because it's not yet. I think the client doesn't want to disclose too much. But if we look at this, we have these numbers I was telling. We have something like below 10 watt of heat that comes per square meter of floor from outside. So and the other building I showed you, we have a recent project where we were assessing, it was about 150, not 10. So just on the passive design of the facade, you already have a factor 5 to 10 of gaining if you reduce this this. And I think there is now, I would say, the new I think the new tendency is that people have realized that they should not glaze as much, but still there is no mandatory requirement that make that you can allow people to do this still. So I think what is important to me is not only it's to teach more and better to the architects, because we have the same problem in Europe with the architects. Whenever they can avoid a shading, whenever they can increase the glazing, they do it, I can tell you. But we have such stringent norms that they don't have anymore this freedom of doing any stupid or crazy thing, So that means as an engineer, you are there to help them in keeping in line with the stringent norms. So I would say, I think in India, to me, I'm convinced that in the midterm, mandatory requirement for building design must be there with more stringent. For instance, ECBC 2025 be something much more stringent on passive design. But if you see the new, I don't know if you are aware of the new India Cooling Action Plan, they mentioned very clearly passive design as one of the options to be looked at. They mention Econivas Samhita to be applied not only for residential, but to be applied generally as a principle for building envelope. So I think there is a trend. Now the trend is one has to put it more mainstream, you know.
Thank you.
Welcome.
That provides a few insights. Thank you.
So Prasanji, there are a few questions on monitoring and
yeah, so the question says, what are the various instruments and parameter monitored for your simulation result validation, and what extent instrument put in place for readability of data captured? So for example, the case study what was shown for Aranya Bhavan, most of the instruments like a lot of electrical measurements, electrical data logger put at various places for say to get all the consumption for each component for chiller, pumps and all. Flow meter to get the exact performance of the chiller COP. And then the temperature, humidity loggers at certain places and even the outside. Lux meter, we have not shown that in the result, but we also did some lux level measurement, so lux meter and all. So then for temperature in measurement in Rajkot, we also did globe temperature measurements so that we were able to calculate the operative temperature. So air temperature and operative temperature, we use the combination of both to get the operative temperatures. These are the broadly the instrumentations and the parameters measured. Does that answer?
But maybe I would just add something. Before doing an energy audit, you can get the energy bill. And the energy bill in the case of Aranya Bhavan is the total energy, the 43 API value is based on the meter. There is no need of any instrument. You just measure, you just look at the bill. If you get the monthly bill, you can directly know the EPI of your system, including everything. Then after, if you say there is a lot of watering, blah, blah, etc., other things, then you should go a little bit more in detail. But basically, any building of some size in India should have its own EPI, let's say, disclosed somehow. Because there are too many. If you see, for instance, just to give you an idea about the paper published that Prashant wrote, and I was a co-author of it on Aranya Bhavan, has been read 10,000 times in ResearchGate. 10,000. Can you imagine? And why? Not because we are Nobel Prize. That's not. It is because there are very few published documents with actual measured data. Most of the publication and papers are on predicted data, but nobody checks after. So it's very nice to say we are reaching 15 or 20, but then get it measured. You don't need to measure. You just ask the bill, the utility company to give you the bill. And if the client is okay, then you get it and then you can check. So I think there is something to already just, if you already get just the bill, you know already where you are. You know, if it's 300 or if it's 50, you will see it directly. So I think that before going to very sophisticated, we did that in Aranya Bhavan purposely because we wanted to really show that in a detailed audit, we can better explain the breakup, and also because we got results which were luckily or because Prashant did a good job also on the simulation, and during the charrette, we did a good job in convincing the clients to do simple things. This building has nothing special. There is nothing from the moon. Everything is simple. Everything is available on the Indian market. There is not a single imported component, apart maybe from the chillers, which often come from abroad. But generally speaking, I think the basic thing is a good coherent design with a rational passive design, even though this building doesn't have external movable shading. We were not able to convince, but still we are getting, if you calculate the heat loads, we are still quite low in the heat loads from outside. And then after, the system is reasonably designed. So the whole thing, and if you just look at the meter, that's how you get the 43 kilowatt hour. You don't need to go for a detail. So I would say pre-audit, getting hundreds, thousands of building and getting just the bill and getting, okay, this EPI actual, this is 200, this is 60, this is 50. Then you know that 200, you have to go and do something.
Yeah, so one of the other objective of monitoring was to also see how the things are performing and is there further scope of improvement in terms of operation and maintenance part. So for example, we came up with a few suggestions for air conditioning system operation based on the monitoring. So there was some regular maintenance was required on the condenser side, the cleaning and all. The temperatures difference were quite less, I would say. So there were few suggestions came out of the monitoring to further improve the performance also. So so that is the kind of course, what Pierre said, overall picture you can easily get through the energy bills. So, and then you can quickly compare what you predicted and what you are actually getting. But just to, if you want to see things in more in detail and see if there is further scope of improvement, then this type of monitoring certainly helps.
But then, of course, if you have a building at 300, you know that if you gain 10%, it is 30, right?
Yeah, that's
if
true.
you have a building at 43, we did it more by consciousness that we wanted to really be sure that we could not do even better, but actually it was already quite good with what was possible. Yeah. But if we gain 10%, then we gain only 4. So I mean, what should be there is that there should be a kind of priority list that wherever you get the energy bills for building, you have the one which are 150 plus, they have to be audited and they have to be scanned. And I think in some of the states it is done somehow. So, but it should be pushed further, I think.
Yeah, so I think we should move quickly. There is another question. What cumulative SHGC considered with Windows frame for simulation input? So I would say that we don't give SHGC with frame. So we define SHGC for glass and its other optical properties. We define the frame material and its conductivity and the parameters. The SHGC is calculated through the simulation. The overall, the combined, you can say SHGC.
Okay, so if there is no further questions, so we can move ahead, right?
Excuse me, I do have
please.
a question. This is Sumedha. I have a question regarding the radiation, the radiation asymmetry. While you do the having a thermal comfort into an enclosed space. So basically in general public office plan, and you have a centralized AC, and the sitting arrangement maybe asymmetric or asymmetric, which are nearing about the envelope. The amount of the heating, cooling requirement will never be the same as those are centralizedly putting in a different spaces. So the heating the heating or cooling asymmetry is a very much challenge when you have a centralized AC and you have a just generic office plan to have a better thermal comfort during the office hours.
You know, it comes back again to the heat gains through the facade. If you have, let's say, very efficient solar protection, dynamic solar protection, and if you have less window to wall ratio, all this becomes less important because you are, if you get 10 watt per square meter on the floor in heat gains, and if you get 12 on the other side because it's a little bit more and 8 on the other side, this will hardly change, because if you think you have the same internal gains, but the moment you have fully glazed, I fully agree. I mean, it's just not the same. On one side, you have maybe 150 watt to remove, and on the other side, you only have 50 maybe. And that's for sure that if the building is poorly designed, then you have to deal with that. That's the issue. So, and also another thing also that if you have water-based cooling, like radiant panels or slab cooling, but radiant panels, let's say, radiant panels are much faster to adjust. So it's much easier. You can have localized control much better than when you work with all air systems.
Okay, thank you.
Welcome.
I think another question regarding the simulation tool. So I think it's Design Builder, right?
Yeah, so Design Builder based on Energy Plus. So the simulation engine is Energy Plus, which is kind of free. Although the interface for it, Design Builder, is not free to use, but it is quite, I would say, easy to use. Otherwise, the Energy Plus interface is JAWS based, and then it's very difficult to model things in Energy Plus alone. So you need a good graphical user interface for that. Thank you.
Okay, so let's move ahead. Yeah, so thank you, Mr. Pierre and Prasad, for the wonderful introduction of the simulation tool, starting from the basic steady state simulation and then various case studies. So with this, let's move ahead. So the last session is, so I hope my slides are visible.
Yes.
Yes.
Okay. So the last session is on the integration of building physics in the heat transfer course. So in this, basically, we will be talking about briefly the content of the book which is developed, and then take a few examples. One is related to the conduction heat transfer, another one is related to the radiation heat transfer. Just to give you an idea, like what is there in the book. So as discussed by Prashant earlier, that during the BEEP camp for educators, so it was felt that there is a necessity to teach fundamentals of building heat transfer or building physics to the engineers. But the major problem as far as engineering education is concerned, that we have a certain set of core courses, professional core courses, and it's really difficult sometimes to introduce courses like this, like building physics or building heat transfer or building energy efficiency, especially in core engineering branches. And also if you float, let's say, elective courses on this, so I mean, whether students are interested or not, so that's another story. So with this in mind, so it was felt that let's start with something where we can actually incorporate the example related to building heat transfer in the existing courses. So one such course which is there in almost all the universities is that heat transfer, which is taught to the mechanical students generally, and obviously the heat transfer course is taken by chemical engineering and other also. So we started developing a few numerical problems which can be incorporated along with the as a tutorial problem or example problem to explain basic concept of heat transfer, and at the same time explain them about the building physics or give them basic understanding of the building heat transfer. So so we developed around 20 set of problems, and the unique aspect of this problem is that they are all developed considering the real case studies, and and the examples are taken from the India, and most of them are basically the case studies. Say, for example, Prashant was discussing about the Aranya Bhavan and the Smart Ghar, Rajkot. So there are many examples from these monitoring and case studies there in these numerical examples. So the data is completely mostly taken from the monitored data, and also some of them is taken from the simulation data. So as far as problems are concerned, so these problems we have tried to map it with the course content. So since we have a mix of engineer and architect here, so I would like to stress here that it's useful for both engineering students as well as architect students. So let's say, for example, if I talk about engineering students, so all of us teach them like conduction, basic modes of heat transfer, like conduction, heat transfer. And when we talk about conduction, heat transfer, so basically we discuss the concepts like thermal resistance, composite wall, U value, etc. Right? And then so we can teach them these concepts, and we can while teaching them, we can give them, like in general also we have tutorial problems, right? So while teaching these concepts, and along with that, we can take some numerical example problems, and these numerical example problems will are developed in such a way that they will give a very good insight of the building physics or the building heat transfer to the students. So in one sense, they will be also be motivated, or they can be means based on this, they will be also looking for or the building profession, or the this building design profession as one of the alternative for them. So, and as far as architecture students are concerned, so they study about all these passive strategies and all these concept related to building or building physics. So if we can teach them some of the basic concept of heat transfer, I'm sure that you must be teaching them probably some of the basic concept of heat transfer. So they by doing this simple calculation and solving this simple numerical examples, they will also get a kind of feel how a simple strategy can have a impact, and they will be able to feel it quantitatively. So these 6 set of problems, basically they talk. So each problem is unique in a sense that it talks about one of the important aspect related to building physics. So if you see these problems, so these problems talk about the effect of insulations, and what is the importance of insulation in the wall, roof, right? And what are the various types of building wall types, and what is the effect of different wall types on the cooling load. Similarly, problem 5 talks about the effect of different roof construction which are widely used in India, right? So how things get changed when you switch from one roof construction to another roof construction, right? So accordingly, so it can help identifying the appropriate or the most suitable roof construction. Obviously, the cost aspect and maintenance aspects is another concern. So, but all these aspects are probably discussed as a remark of the numerical problem. So after each numerical problem, we have kind of discussed what is its implications, and kind of detailed discussion is provided at the end of each problem. Similarly, problem 6 talks about the roof surface absorptivity and its effect on the heat transfer and the cooling load. Now, then we have 3 set of problem where we are talking about multi-mode heat transfer involving conduction and convection heat transfer, where and these can be taken up when we talk about the concept of thermal resistance, composite wall, when we talk about rate equations like Fourier law, Newton's law, cooling law, right? Or when we talk about the radiation laws. And also when we discuss about different correlations for heat transfer, convective heat transfer coefficient. So, and then while discussing these core concept, we can teach them about the effect of air tightness on the building structure, on the cooling load in a building structure. Similarly, effect of wind speed on the heat transfer, and also as far as monitoring is concerned. So one of the important parameter while we do some kind of thermal comfort monitoring, so is to measure the room air temperature, right? So how the radiation can affect the air temperature measurement. So this is another example by which they will understand this. Then we have another six set of problems where which are focused on the radiation heat transfer, and which can be taken up while explaining the concept related to the rate equation associated with radiation heat transfer, and discussing the safe factor and the radiation exchange between surfaces. So so the radiation asymmetry which ma'am was talking about just a moment back. So we have one example there related to radiation asymmetry. Let's say a person is sitting near the glazing and a person is sitting far away from the glazing. So how the thermal comfort is affected, right? Or how the heat transfer or the thermal comfort or the radiation, this energy balance changes. Then it also talks about the effect of building orientation, as Lal sir was talking about earlier, right? North-south orientation, east-west orientation, and also the concept of SHGC, right? How SHGC is actually calculated. So so there are numerical examples where people can actually calculate what is the SHGC based on the fundamental understanding of the heat transfer and different modes of heat transfer. Then since the morning we are talking about radiant cooling system and conventional air cooling system, conventional AC system. So there are examples where we are talking about the effectiveness of radiant cooling system, and there are examples where we are talking about the comparison of conventional air AC system and radiant cooling system. So we'll see one such example today, and also how the thermal comfort is affected when we change floors in a particular building. Let's say if someone is sitting at the top floor and someone is sitting at the bottom floor, means ground floor. So how the thermal comfort will be affected. Then we have three set of problem where we are comparing the single pane glass window and double pane glass window. So it's a very comprehensive problem, especially this one, because it talks about so many aspects, like from the detailed sketch, like from the basic concept of heat transfer, how this SHGC is calculated for single pane window and double pane window. Then introducing the concept of sole air temperature, what is the effect of window to wall ratio, right? So, and then in the discussion, we are also talking about the necessity of window and how these different factors like cooling load, natural ventilation, and daylighting plays a role while selecting the window to wall ratio. Then there are two multi-mode heat transfer problem where we are also talking about the importance of external shading, right? So so basically the impact of external shading is shown there with the help of basic sensible and latent heat in a multi-mode scenario concept. And also a comparison is made between external shading system and the double pane glass window, and just to see which one is more effective. And then there is a numerical problem on basic heat balance and the thermal comfort, and how the building wall insulation plays a role and it affects the thermal comfort. Okay, so this is the overall idea about all the 20 problems which we have developed and which are there in the book. So probably we will share a copy of this book later with you. And then I'll just quickly go through two numerical problems just to give you an idea like how it is developed and how simple concept of heat transfer can be used to explain some or the other concept of building related or building physics. So all of us know that we have different modes of heat transfer: conduction, convection, and radiation, right? And there are many applications related to heat transfer, so which are widely discussed. So in all of our curriculum, we study so many example problems, including furnace, boiler, etc. Right? But hardly we talk about building when we teach heat transfer. So so the idea here is to give them a flavor of building also, along with other engineering applications involving furnace, boiler, etc., the conventional problems. So this is just a basic of conduction rate equation or the Fourier's law. So probably all of us know that, but so the idea here is that we can teach these concepts, but at the same time we can include the building physics or building related stuff wherever we can, right? Say for example, when we talk about conductivity, we can also talk about building materials while teaching the thermal conductivity aspect. And then we also talk about concept of thermal resistance, right? And we also talk about the overall heat transfer coefficient, which is U value. So which we call thermal transmittance in case of building heat transfer. So all of us talk about this when we go through the heat transfer syllabus or the course content, right? But the difference here is that while explaining these concepts, we can actually talk about the U value concept in terms of building also, right? So how this U value play a significant role, and it is actually practically also important, right? So we simply tell them how to calculate the U value, but we hardly tell them where it is used, right? So building is one such application where there is a direct application of the U value, right? So all the building codes nowadays talk about U value. So I'm quickly going through it because of the time constraint. So probably if you have any concerns, so we can discuss it later also. So with this, so I have picked one of the example problems related to the concept of thermal resistance, right? So in this particular problem, we are taking 3 roof constructions, right, which are widely used. So first one is the normal roof construction, right, with cement, concrete, RCC slab, and cement plaster. Then the second is roof with reflective tiles. So you have a reflective tile at the top. It can be a China mosaic tile or whatever. And then the third one is a painted roof where we have a reflective paint at the top exposed surface. So again, this example is related to the Smart Ghar project monitoring, which was explained in the previous presentation, right? So all the data is taken from this the site, and it's a realistic data, right? So so a typical time is considered, let's say in the month of May, which is a summer month, at 1 p.m. So these are the environmental conditions: 37 degrees Celsius and 1036 watt per meter square solar radiation, incident solar radiation. And room is supposed to be maintained at 27 degrees Celsius. So the problem here is to find out the heat flux through the roof, right? Because we are talking about different roof configurations, and also the temperature at the inner and outer surface of the roof assembly for all the 3 roof configurations. And all the properties of different materials are given in this particular problem. So by simply applying the concept of thermal resistance, so this inner surface temperature, outer surface temperature, and the heat flux can be obtained for all the 3 cases, right? And so this detailed discussion is there at the end of problem. So you can see here from the table that for the normal 3-layer roof construction, so the watt, so the heat flux is 102 watt, right? Whereas if you see the other roof construction, so it has decreased significantly. So almost 50% decrease can be seen in the heat flux. Similarly, there is a significant decrease in the inner surface temperature as well as outer surface temperature of the roof, right? So, so now it's very clear that once the inner surface temperature is lower, so you will have lower mean radiant temperature, obviously, right? So it will have, I mean, so you will have better thermal comfort inside. And you can, so from this, it can be concluded that roof with reflective tile or painted roof can be your preferred choice, right? But obviously there are issues associated with it, like cleanliness, cost, and life, which should be taken into consideration while designing a building or while selecting the proper roof configuration. And I mean, roof reflective coating can be preferred because it doesn't add any mass on the roof. But at the same time, it leads to a very low inner roof surface temperature as well as heat flux. So means the building cooling load can be reduced significantly. And then this is a typical climate classification of India, right? So when we talk about the U value, so this is just an it is taken from ECBC. So you can see here that for different climatic conditions for roof and wall, ECBC specify the maximum U value which is permitted for commercial buildings, right? So now, so the U value which we talk about, the overall heat transfer which we talk about during the course, so it has direct application here, right? So and it has a lot of effect also in terms of actual building cooling load. So you can see here that there is a building as business as usual construction and a ECBC compliant roof and wall. So here the U value is significantly higher, right? And in this case, the U values are as per the ECBC suggestions. So you can see here for roof, here composite climate, it is 0.261, and for wall, it is 0.44. So if this is the case, so you can see here that heat inflow through roof can be reduced by 90%, and through wall it can be reduced by 70%. So it has a significant impact. So means we can have a kind of small exercise for students, so where we can ask them to decide, let's say, for example, the thickness of XPS or the insulation in a multi-layer wall arrangement or a wall assembly, so that you comply with the ECBC, right? So you can have, you can analyze for different XPS thickness, what is the U value, and then the moment this U value goes below 0.44 or reaches 0.44, that particular insulation thickness can be suggested, right? So that your building or your wall comply with the ECBC. So these are simple exercises, but this will give them a kind of flavor of the building physics, and also it will be very interesting for them also to learn the basic, the basic concept, right? Otherwise, we simply teach that there is something called U value without any practical use of the U value. Then I would like to take another example related to radiation heat transfer. So this is a very fundamental. All of us know that we have the summation of your absorptivity, reflectivity, and transmittivity is 1, right? And there is something called black body, opaque body, and semi-transparent mediums. And then we have the rate equations associated with radiation heat transfer, where we calculate the emissive power. And then we use Stephen Boltzmann for black bodies. And then for real surfaces, we have this emissivity coming into picture. And then in a multi-mode scenario where you have convection as well as radiation, so this Q can be calculated like this, right? And then we also talk about the shape factor, right? Which is the fraction of radiation leaving from a particular surface and which is intercepted by another surface. So and this shape factor we usually calculate either using the correlations, which are not always available, or by using some charts, right? So now this is very similar to our building, right? Say for example, if you're talking about a particular room, so this I can be your floor and J can be your ceiling, right? Similarly, I can be a floor and J can be your wall. So so based on this, means the shape factor between the wall and the ceiling or wall and the roof can be calculated, right? And once you know that, and you can also calculate the mean radiant temperature, right? And also you can calculate how much radiation is being exchanged by the human body with the building envelope. So the radiation heat exchange between two surfaces, let's say one surface can be the human body, another surface can be the building envelope. So it can be obtained like this, where we consider the surface resistance as well as space resistance, right? And this can be further used to determine the heat loss by radiation from human body to the envelope, or from envelope to the human body. So for this, I have selected one particular example where we are talking about conventional air conditioning system and the radiant cooling system. So now for this particular example, we have selected Raipur as one of the location, right? And all the dimensions related to the room is given, and all the radiative parameters like emissivity and other heat transfer coefficient, skin temperature are given. So the objective here is to find out what is the total heat transfer from the human body to the building envelope for both the cases, right? So in case of conventional air conditioning system, we are maintaining the indoor air temperature at 27 degrees Celsius, right? And in case of radiant cooling system, we are maintaining the indoor air temperature at 30 degrees Celsius. So remember that in case of radiant cooling system, it is 30, which is 3 degrees higher than the conventional air conditioning system. So in both the cases, the radiation exchange from the person to the ceiling and wall and floor all are calculated, and also the convective heat transfer is calculated. So, and then once you have this convection plus all radiative component, so you can add them and you can get the total heat flux from the person. So it comes out around 65.27 watt per meter square in case of a conventional air conditioning system, and it comes out 66.78 watt per meter square for room with radiant cooling system, right? So from this we can see that in both the cases, right, for conventional air conditioning system also and for radiant cooling system also, see the heat lost from the human body is more or less same, right? It is almost equal to 65%, 65 watt per meter square. So it means that in both the scenario, whether we use the conventional air conditioning system or the radiant cooling system, person is going to have the same level of thermal comfort, because he or she is losing the same amount of heat. And remember that this heat of 65 watt per meter square is almost equal to the heat lost by a person who is simply sitting on a chair, right? So if a person who is sitting on a chair is generating around 65 watt per meter square, and at the same time he or she is losing that same amount of heat, so it means that person is in thermally neutral state. So it means a comfortable state, right? And this thermal comfort is achieved in both the cases, in case of conventional air conditioning system also and radiant cooling system also. Now the difference is that in case of, as I said earlier, in case of conventional air conditioning system, the temperature of the air is maintained at 27, whereas in case of radiant cooling system, it is maintained at 30 degrees Celsius, right? So there is a 3 degree temperature difference between the two systems, right? And from our basic understanding, we know that by increasing 1 degree temperature of the air, we can save around 6 to 10% of the energy consumption, right? So in that sense, I can say that by increasing the air temperature by 3 degrees Celsius in case of radiant cooling system, we can save around 30% of the energy, right? So that is why we say that radiant cooling system are more efficient, right? So this is what we are discussing since the morning. Okay, and with the help of this particular very simple example, we have demonstrated this. Okay, so I think with this, I would like to stop here, and we can discuss if you have any question. Thank you.
Hi, Dr. Udairaj, one quick question.
Yeah, please.
So would you would you be sharing these slides or the recording with the attendees?
So we'll discuss this probably and let you know.
Sure, please. Thank you.
Yeah.
It makes, it will be so helpful for all of us.
Yeah.
Thank
And
you.
in any case, I will be sharing with you the copy of the book. So, and most of the case studies which were discussed in the previous presentations, so they are available already online, right, Prashant?
Yeah, so I think like I have no issues in sharing my presentation. Also, maybe I can quickly show you our BEEP website. Let me share my screen. Yeah, so I hope my screen is visible.
Yes.
Okay, so it's www.beepindia.org. Then you have a resources tab here. And there you can find all the things like the two case study which I presented. For example, let me show you case studies. So you will get all the details. There are videos also, so it would be even easier to understand. And there are few additional case studies, like for example, the hospital building case studies there, and some of the technical papers which were where you will find more technical details, what was not covered in the presentation. So those also you can find. And some of the things like the code and everything. So for example, the residential code we were talking about, Ikonikova Samhita, the code document you can get, the compliance tool is also available. And there are sort of other things as well. So if I recommend everyone who's interested in getting to know some more information. There are a good set of resources available on the website, which you can get at one place, I would say. Then there are design guidelines also. There is something on building insulation material as well, quite detailed things. And then things on external movable shading, radiant cooling. We also have done a lot of training program in specific things, like for example, energy simulation training program we have done. Radiant cooling, there was a 2-day specific program, earth air tunnel. So for all those programs, so all the presentation and like all the technical material is available on the website. So I suggest that whoever is interested can get a lot of good information from the website. Of course, the book will also be available in public domain, what Dr. Udairaj was showing. So, yeah.
Thank you. And what about Mr. Aliko? If I'm pronouncing his name correctly, the presenter from
Pierre.
Pierre. Yeah, sorry. Is he would he be comfortable? I found that his presentation quite unique. Thank you.
Yeah, so I will check with him, and we have email IDs of all of you. Then I will check with him and share.
There also, no problem. We can share the presentation. We share it just in a PPS format. That's it. That's all.
Thank you, gentlemen. Okay. Thank you so much.
Okay, so just one point. So I will be sharing feedback form at the end and through mail. So please give your suggestions. Okay. Okay, so we'll see about this PPT and also I will mail you. So there is.
So I think what we will do, we will share everything with Dr. Udairaj, and then he will be emailing you all the presentations.
Maybe just one thing also, I think it's quite impressive to see so many people following this on a Saturday. And I must say, I think that if you feel there is an interest, I think we should try to put in place a kind of a platform going beyond this, in a sense that Dr. Udairaj has been the pioneer in writing this, in a sense. And I think some of you could also volunteer for some other things about building physics, about HVAC, about things. And we could, of course, our team BIP could help you also in that, in a sense that, because I think the nitty-gritty of writing is not our job, in a sense, because you are as teachers much more performing to write a book than we would do, in a sense. We could do a more generic book, but if it be of the
Okay, so I will be sharing the feedback form. So kindly provide your inputs there or comments there. And also once the book is out, so I will be sharing that copy of the book also. And in any case, it is going to be available online. So with this, I would like to propose a vote of thanks, right? So on behalf of IIT Bhilai and Department of Mechanical Engineering, first of all, I would like to thank the team for allowing us to organize or host this workshop and sponsoring it. I would like to thank all our speakers, Mr. Ashok Lal, Mr. Pierre, Mr. Prashant, for accepting our invitation and providing such an enlightening talk, highlighting the various aspects of building heat transfer, building energy efficiency, the role of engineers and architects, and what are the way forward. So I'm sure that all of us who attended the workshop have been greatly benefited by such insightful talks and discussions. I'm especially thankful to Dr. Shamir, Mr. Prashant, Mr. Mohit Jain for their tireless effort and support since the beginning and also in organizing this workshop. And I would like to thank our HOD, Dr. Shaumya Gangopadhyay also, and my faculty colleagues for their cooperation. And also, I would like to thank the scholars in my group, especially Jeshnu, for his cooperation throughout the event. And finally, I'm also very thankful to all the participants for attending the workshop and devoting their precious time, especially on Saturday. And I hope we'll do this, do much more such programs, especially in the offline mode in near future. So thank you very much, everybody, for attending this. And I'll just share with you the feedback form. So kindly provide your inputs and comments and suggestions.
Thank you, sir.
I will share the certificates later, probably. I'll send you through email.
Thank you, sir. Thank you so much. And on the PRS remark, I would be happy to work with the group, collaborate with Shivnadar University, and taking these things forward. These are important for our future generation, even our generations for that matter. We still have 40 good years to live.
Yes.
Thank you so much.
Yeah. Thank you.
Thank you, sir. Thank you. The session was very interesting. So I got more information about heat generating in buildings. Thank you, sir.
Yeah. So, Prashantji, is there anything else I missed?
No, I think everything is covered. And from the project side, from the Indosys BEEP team, I would say thanks to Professor Udairaj for conducting this event, all the effort made to invite all the people and organizing and sort of hosting the event. So it's a good effort, and I would recommend that all the participants take the advantage of this book and try to see if how they can utilize like whatever the content is there, how it can be utilized in their curricula, and how to make best use of it.
Yeah, I think it's a very small beginning, but I think it's a good start. So I think we should do it more.
Yeah, I would just like to congratulate Dr. Udairaj, because he has been, we interacted 2 years ago now, the first time.
Yeah.
Also harsh, in the sense that when somebody comes from an IIT and comes with a lot of equation, plenty of things, then you think, oh, there are too many things. We have to make it simpler. And I think, Dr. Udairaj, you have been really excellent in catching our proposals and doing it at the same time very rigorously and at the same time very practical oriented, I think, and to make the interest of the students. So congratulations.
Thank you. Yeah, so I think we can stop now. Yeah, thank you, Prashantji, and thank you, Pierre, for your time and nice words. Thank you. Thanks, everybody.
Okay, thank you, everyone.
Thank you. Bye-bye. Thank you very much,
Bye.
Dr. Udairaj, Prashant, and Pierre. Thank you so much. Wonderful. Thank you. Bye.
Thanks. Bye.